Hello, good morning. Can you hear me in the back? Okay, thank you. So I'm Jitendra Malik. On behalf of the Electrical Engineering and Computer Science Department, I'd like to welcome you all this day. We can all see the rains, and I'm sure there are many of your colleagues who are on the freeway somewhere, and I hope they will eventually manage to make it here, but we should start the program. So we're going to start with a few remarks about the state of the EECS department. Then we'll have an award ceremony for distinguished alumni, and then we'll get on with the formal program of today. So let me start it off with a report on the state of the department. So first, the leadership. I'm Jitendra Malik, I'm the chair of EECS. My colleagues Jan Rabai and Jim Demel, whom you'll see later on in running different parts of the program, they are respectively chairs of the EE division and the CS division. So where does EECS at Berkeley stand today? So we are the largest department on this campus in virtually any dimension you can think of. More than around 110 faculty, about 650 graduate students, and 2,220 undergrads. I'm sure this number is outdated as we as you all know, right now is an era of great demand for undergraduate education in computer science, and this is both a sort of a pleasure as well as a problem, and we have to deal with both aspects of this. How's the department doing? The standard measures of reputation are how we do at various surveys. So US News and World Report surveys both graduate programs and undergraduate programs. So in graduate programs, in electrical, electronics, in communications engineering, we are tied for joint first with MIT and Stanford. In computer science, again, we are tied for first with Berkeley, CMU, MIT, and Stanford. Interestingly, we are second in computer engineering, but we don't have a computer engineering program. Okay, as far as I know, nor does Stanford or MIT. So this is a fictitious program, but we are still very good at it. Okay. That's the benefit of reputational surveys. They don't have to rely on reality. Okay. Okay. Then this is how we do on undergraduate programs, and there we are typically ranked third, which I suspect is partially due to the fact that the student-teacher ratios, given that Berkeley is a public university, have to be more adverse than our private competitors. Okay, so that's where we stand according to the external world. Other measures of success are how various awards garnered by our faculty, and there is a long list on the department website which I won't go through, and this is just a sampling of some of the awards, and I've highlighted here a few of the recent awards. So Chen-Ming Hu won the National Medal of Technology. I was talking to him at breakfast, and he's fortunate to have been able to receive it from President Obama. The Silicon Valley Hall of Fame, another honor for Chen-Ming, who is elected there along with various other of our colleagues. And Sujay King Liu, the previous chair of the department, received the SIA University Research Award. And underneath, in sort of this dim font, is the listing of, we have 36 members of the National Academy of Engineering, 12 members of the National Academy of Science, 18 American Academy of Arts and Sciences, and so on. But I want to now report, just as a random sample, the awards that our faculty got yesterday. Just a random sample, 1 out of 365 days in the year. Okay. So yesterday, to the National Academy of Engineering, Sujay King Liu was elected for contributions to the FinFET and its application to nanometer CMOS technology. And Kathy Yellick was elected for software innovation and leadership in high-performance computing. So this is one of the highest honors that any engineer can get in the United States, and we are pleased to have 2 of the awardees in our department. But that's how yesterday morning began. In the afternoon, about the winners of the Chan Zuckerberg BioHub initiative. So some of you may know about this. Chan Zuckerberg, Zuckerberg is Zuckerberg of Facebook. And this is an initiative aimed at curing disease. And they have given out awards to faculty in Berkeley, Stanford, and UC San Francisco. So those are the 3 institutions which are part of this. And there were 12 awards that Berkeley faculty received. Of them, 5 were received by faculty in the Department of EECS. And you will hear from one of them, Michelle Mahabes, later on in this afternoon, later on this morning. What's interesting is that this is about biology and medicine. And we are supposed to be a department of electrical engineering and computer science. And yet, we have the largest number of awardees for this, which tells you that the E is not the same E that you used to think about, and CS is not the same CS you used to think about. These fields have evolved considerably. So one measure of that is, for example, graduate student applications in the department. In computer science, 60% of the applications this year for doing a PhD were in some area of AI or machine learning or vision or robotics. So the field is changing. Where it goes, we do not know. We are going to speculate on that later on in the morning. We are continuing to hire new faculty. These are some of them. These are faculty hired last year or in the coming year. And they represent Chunlei Liu, Ricky Muller. She was one of the winners of the Chan Zuckerberg BioHub Award. Girija Ranade, who's coming up shortly. Moritz Hart in learning. Sergey Levin in robotics. Jonathan Reagan Kelly, who works on special purpose architectures. We have a whole slew of research centers, and often in these talks, I might run by a list of 40 research centers that we have. We are not doing that today. What I'm going to do is to just present a few of them, and then you'll get more detailed coverage of these as the morning and afternoon proceeds. So among the research initiatives in this department, I want to mention AI, artificial intelligence, where we have always had a number of faculty, but somehow all doing work as individuals or in groups of 2 or 3. And we have tried to pull it all together. And as you see, today is a time when AI is really in the public eye. And there's a lot of hype associated with that. And we believe that we have only scratched the surface, and there's a lot which needs to be done. And our slogan is that much more research is needed to make AI both capable and trustworthy, not trustworthy, maybe that too, but trustworthy. And today, the program is in fact focused around AI. Another of our centers is on sort of brain-machine interfaces. So this is where research on natural intelligence and artificial intelligence sort of go on a continuum, but based on a substrate of hardware innovations. And again, I think Michelle Mahabes was going to talk to you, so you'll hear more about the research developments in this area shortly. Many of you have participated in the AMP Lab. This has been justly famous. It has had a very big impact in industry, and it's really been about batch data to advanced analytics. The style in many of these centers is that we run them for 5 years. We have a start off, we have an end date, we have a end of term party, and then something new is started. And in that spirit, the AMP Lab has given way to the RICE Lab, which is on real-time intelligent secure execution. And the key thing here is moving from batch data to live data, online decision making for real-time decisions. And this will, of course, continue for the next several years. Many faculty are part of it, and it has been generously sponsored by several companies. We have a Berkeley Center for Computational Imaging. This is an interesting center. It involves faculty both in EE and in computer science. Laura Waller, who's one of the leads here, she was one of the winners of the Chan Zuckerberg Award. And basically, this is about all aspects of imaging. So there is the optics aspect, the software aspect, as well as the applications largely to various biological problems. And I'll conclude with this sort of word salad of different topics that our department works on. We will today focus only on a few of them, and now I want to turn it over to my colleagues for the award ceremony. So Jan and Jim. Okay. Jan Rabai, the E Division Chair.
All right, good morning.
Oh, I should not disappear.
No, well, this is fine. So this is one of my favorite parts. I'd like nothing better than giving out awards. So that's what we're going to do right now. The ECS department is actually honored to present our distinguished 2017 Distinguished Alumni Award in Electrical Engineering and Computer Sciences. And this year, distinguished alumni are Professor Ananta Chandrakasan, Professor Gary Miller, Andy Hertzfeld, and Wayne Dye. We are delighted to have him here with us today, with the exception of Wayne, who had actually at the last minute had to cancel because of a trip to China. But we're actually honored to have his wife here representing him. So we'll start with our first recipient, Professor Ananta Chandrakasan. Ananta received his BS, MS, and PhD degrees in electrical engineering and computer sciences in Berkeley in 89, 90, and 94, respectively. I remember very well, I was a very junior faculty member at that point in time. His advisor was Professor Robert Broderson, who was unfortunately unable to join us today. Since receiving his PhD at Berkeley, Ananta has joined the ECS faculty at MIT, where he actually has served for the last 5 years as department head, and where he is also currently the Vannevar Bush Professor of Electrical Engineering and Computer Science. Professor Chandrakasan is renowned as a phenomenal teacher as well as a world-class researcher. He has co-authored multiple textbooks: low-power digital CMOS design, digital integrated circuits, and subthreshold design for ultra-low power systems. His research in the areas of ultra-low power circuit system design, energy harvesting, energy-efficient RF circuits, and hardware security have garnered him many awards, including the 2009 Semiconductor Industry Association University Research Award, the 2013 Donald O. Peterson Award in solid-state circuits. He has been a great leader for the profession, serving in many capacities for the IEEE SIC conference as an example, and he also has served as director of the MIT Microsystems Lab from 2007 to 2011. He's an IEEE fellow. He was elected to the Academy of Engineering, and now joins us as a UC Berkeley ECS Distinguished Alumnus. We are honoring for innovative personal and institutional leadership in teaching, research, and profession. Ananta. You want to say a couple of words?
Thank you so much, Jan. I'm really deeply honored and humbled to receive this Distinguished Alumni Award in Electrical Engineering from UC Berkeley. This honor is incredibly meaningful to me, having worked here with professors who are pioneers in the field of integrated circuits and systems. I would sincerely like to thank the many wonderful professors who taught me and mentored me, and the staff members who supported me from my undergraduate years through the PhD and beyond. My faculty mentors here always challenged me and helped me focus on high-impact research. I was extremely fortunate to be an undergraduate researcher in the lab of Professor Robert Broderson, who was also my academic advisor. I went to ask him for advice regarding a summer internship opportunity, and instead, he very generously offered me a spot in his research group. That's actually where I also worked very closely with Jan. I was very lucky to be in the right place at the right time when energy efficiency of electronic circuits was just becoming a critical issue. And this undergraduate experience actually played an important role in getting me excited about academia. In fact, inspired by this experience, I created a program at MIT which prepares undergraduate students for publishing their research and for graduate school. I was also fortunate to work through my PhD with Professor Broderson, who pioneered the field of low-power digital circuits and systems. And during my PhD, I had the amazing opportunity to work with amazing faculty members, students, and staff on the InfoPad project, which is a mobile multimedia terminal. The project set many benchmarks in energy-efficient design, which is now, of course, very important in mobile computing and Internet of Things. And I've used my experiences at UC Berkeley from the InfoPad project extensively. For example, I've set my own research projects to be highly collaborative and more system-focused. So I'd like to thank Professor Brodersen and UC Berkeley for giving me the chance to be a graduate student here. Also, in the last few years, it's been my privilege to collaborate with UC Berkeley, and it's, for example, working with Professor Sujay King Liu. We brought the Rising Stars to Berkeley, which is an academic workshop for women. Finally, I'd like to just thank my family for their incredible support throughout my academic career. So let me once again thank you for this high and distinctive honor.
So next, we will be honoring Professor Gary Miller. Gary received his PhD here in 1975, and his advisor is Professor Manuel Blum, who is now among his colleagues at Carnegie Mellon. After receiving his PhD, Professor Miller held faculty positions at the University of Waterloo, the University of Rochester, MIT, the University of Southern California, and finally he settled down at Carnegie Mellon University, where he's currently a professor of computer science. So Professor Miller is renowned as a pioneer for his algorithmic contributions to theoretical computer science. His work has impacted cryptography, number theory, parallel computing, graph theory, mesh generation for scientific computing, and linear system solving, my favorite topic, in a major way. His PhD thesis was called Riemann's Hypothesis and Tests for Primality, and it introduced the first efficient algorithm to test whether a number is prime, something we all depend on whenever we use a login. And it laid the groundwork for the Miller-Rabin test with Professor Michael Rabin, which is the main method used in practice for RSA encryption keys, so public key cryptography. His contributions to theoretical computer science also includes his work on the theory of isomorphism testing, the theoretical foundations for mesh generation, and one of his great products there is, of course, our own faculty member, Jonathan Shuchuk, his former PhD student, and his breakthrough results in providing the fastest algorithms for solving symmetrically diagonally dominant linear systems, with lots and lots of different important applications. He's also been awarded the ACM Paris Kanellakis Theory and Practice Award and the ACM Knuth Prize to the creator of problem-solving theory and algorithms. And today, he joins us as a UC Berkeley ECS Distinguished Alumnus. So, Gary, if you could come up. So, the citation is we are honoring him for significant algorithmic contributions to computational number theory, parallel computation, mesh generation for scientific computing, and linear system solving. Congratulations. I will give this to you if you want to say a few words.
Okay.
Or do you want-
I want to take a picture first. So you
Okay, yeah, okay. Quick picture. Excellent.
Okay. I didn't have a piece of paper. Printing on a piece of paper is hard these days, right? So, a second. Get over here. Okay. So, thank you very much. So I'd like to thank Berkeley ECS for this award and honor. It's a very humbling award. And also I'd like to start by thanking, first of all, my mother, who recently passed away, for her encouragement and support. Without it, I would have never done a career in such direction. Third, I'd like to also thank the UC educational system for allowing people of modest means to actually go into the profession. It's the case that for making it possible for California sons and daughters of modest means to participate and collaborate with the world's finest students and faculty. I personally had the opportunity to spend innumerable hours collaborating with other students. This collaboration formed the basis of both my research area and style. In particular, I am fond of the memories I had spent in the local coffee houses with students such as Dana Anglin, now a professor at Yale, and Len Adelman, a Turing Award winner at USC. I would also like to thank my advisor, Manuel Blum, and also I'd like to thank Dick Karp for his wonderful course on algorithms that got me inspired to go in the area. And I'd like to hope that the Californians understand the importance of the UC system to improve the lives of citizens of California. Thank you.
Next, we'll be honoring Wayne Dye. Unfortunately, Wayne was not able to join us today, but we are honored that his wife, Joanne, is here to accept the award on his behalf. We will be playing a video shortly that Wayne has sent us of his acceptance speech. Wayne received his BA in computer science and his PhD in electrical engineering from UC Berkeley in 1983 and 1988, respectively. His advisor was the late Professor Ernest Koo. Professor Koo's son, Ted Koo, is here in his father's stead today. After receiving his PhD, Wayne joined the faculty of the Department of Computer Engineering at University of California, Santa Cruz, where he served for over a decade. Wayne went on to found several influential companies, and today he is regarded as a visionary leader in industry on an international scale. In addition to founding Ultimate Interconnect Technology, Inc., and serving as co-chairman of the board of directors and CTO of Celestri Technologies, Wayne is best known as the founder, chairman, president, and CEO of VeriSilicon Holdings Limited. He has also been an influential leader in the profession as the founding chairman of the IEEE Multi-Chip Module Conference, founding chairman of the IEEE Symposium of IC Package Design, Integration, and associate editor of both the IEEE and Transactions of Circuits and Systems and the IEEE Transactions on VLSI Systems. He was elected as one of the top 10 venture-backed entrepreneurs and one of the top 10 talents of science and technology in China in 2005 and 2007. In 2007, he was recognized as the Ernst & Young Entrepreneur of the Year in China. He now joins us as UC Berkeley ECS Distinguished Alumni. Johan? We're honoring Wayne for his visionary, technical, and entrepreneurial leadership on an international scale.
Dear ladies and gentlemen, I would like to thank the ECS department for choosing me to receive 2017 Distinguished Alumni Award. I'm so pleased and deeply humbled. I want to apologize for not being able to receive the award in person. There is an urgent event in China which I cannot travel back to the Bay Area in time. UC Berkeley has such an enormous impact on my life and career. In particular, my PhD advisor, Ernest Koo, former dean of the College of Engineering, taught his students to focus on big picture, which has influenced me the most. He was the first Asian dean at Berkeley. He went to China with U.S.-Chinese academic delegation in 1973, shortly after opening door to China. He met Deng Xiaoping in Beijing in 1983. As the president of the Berkeley Club of Shanghai, I started Shanghai Berkeley Board since 2011. Chancellor Bergener and Dean Sestry attended the ball. In conjunction to ball, we had 2011 Berkeley Shanghai Biotech Forum. 7 Berkeley faculty attended the forum. In 2012, Dean Jennifer Walsh of Environmental Design and many famous designers who are Berkeley alumni gathered together in Shanghai and exhibit their design project. In 2013, Vice Chancellor Scott Beatty and Professor Connie Chen gave keynote speech at the ball. On November 11, 2011, that is 11/11/11, UC Berkeley and the Zhangjiang High-Tech Park signed an MOU for the research collaboration. On November 15, 2013, Shanghai Zhangjiang Berkeley Engineering Innovation Center, called ZBay, opened at the Zhangjiang High-Tech Park. For the past 2 years, ZBay organized the 2 executive education programs. Berkeley engineering faculty came to Shanghai to give the lectures. This is the lecture provided by Provost Sujie King Liu, former ECS chair, and me on new semiconductor technologies. Berkeley Shanghai Club also helped to establish the partnership between UC Berkeley and the Shanghai Jiao Tong University. I also contribute to establish the Ernest S. Koo Endowed Chair Professor. I was very honored to give Ernest Koo Distinguished Lecture on February 18, 2015, following Andy Grove, former CEO of Intel, William Suleiman, CEO of Angela, and Sahar Sotaja, CEO of Marvell. I want to thank the support from my family, who are also UC Berkeley alumni, my wife, who accepted this award for me, and my daughter, who just got a bioengineering PhD last semester. I want to again express my gratitude to the ECS department and everyone I work with to make all the event possible. Thank you again for your choice and trust. From China, go Bear.
Thank you, John. All done? Okay. Finally, we would like to honor Andy Hertzfeld. After receiving his degree in computer science from Brown University in 1975, Andy attended graduate school here at UC Berkeley, where he received his MS, master's degree in computer science. His advisor was Professor Richard Fateman, and he was also mentored by Professor Marty Graham. Only a couple of years after receiving his master's degree here, he was hired by Apple Computer as a systems programmer. Apple co-founder Steve Jobs would soon add Andy to the Apple Macintosh design team, where he became a primary software architect of the revolutionary Macintosh operating system, which obviously many of us are using, breaking new ground in the use of graphical user interfaces. As Apple's official software wizard, Andy Hertzfeld wrote large portions of the Macintosh's original system software, including much of the ROM code, and if you don't remember, that's read-only memory, the user interface toolbox, and a number of innovative components now standard in many GUIs, like the control panel and the scrapbook. Andy is lauded for his role in the creation of the original Macintosh computer, as well as for numerous innovative companies that he founded after his time at Apple, including Radius, General Magic, and Easel. His contributions to the Open Source Applications Foundation, and his key design work at Google, where he's been working since 2005. As a member of the original Apple Macintosh design team, he has been ensconced in our culture as a technological pioneer, including multiple portrayals in film, like the 2015 movie Steve Jobs, and chronicled in the collective stories found on his own website, folklore.org, that make available dozens of tales about the development of the original Macintosh. Today, he joins us as an EECS Distinguished Alumnus. So, Andy, if you could come up. Great. Thank you. So, I'm going to read the citation. We are honoring him for seminal contributions to personal computer operating systems and technologies, and for entrepreneurial activities that have led to the founding of numerous innovative companies. Thank you again.
Thank you.
So, you can hold it while you speak if you like.
Okay. Thank you so much for this great honor. I started at Berkeley in August of 1976. Started in the graduate department the same year as Eric Schmidt and Randy Katz were some of my co-classmates. And it was an exciting time at Berkeley because just the few years prior, during the Reagan governorship, the department was starved for resources. That was finally receding. They had gotten a PDP 1170 computer with an early implementation of Unix on it. The most exciting thing was a VAX computer, one of the very first super mini computers that was coming the very next year. But the thing I was most excited about arriving here in August 1976 was the personal computer revolution that was just kicking off like 30 miles south of here in Silicon Valley. The possibility of ordinary people owning their own computers and benefiting from them was just thrilling to me. And I was just really excited to be near that while it was happening. I remember the week I got to Berkeley, I started exploring down University Avenue, and I found one of the very first little personal computer retail stores, a Byte Shop, carrying the Altair and the IMSI. I used to walk by longingly every week or so, just staring at them. I couldn't afford the early microcomputers. I went to the first West Coast Computer Fair in April 1977 when I was a graduate student for just about seven or 8 months at that point. And I saw the Apple II, which was announced there at the first West Coast Computer Fair. And it blew me away. I fell in love with it immediately. But it was too expensive for me to afford. It was about 110% of my net worth at the time. So I saved my money, and in January 1978, they had a $400 off sale. That was enough that I actually bought one. And quickly it took over my life. It became more interesting to me than my classes. I knew I wanted to do something with personal computers. Eventually, I started writing programs for it. I got an offer that just thrilled me to work at Apple in January of 1979. But I had put more than 2.5 years into a PhD program at that point. I thought I should get my master's degree. And I wanted to use some of the work I was doing on the Apple II for my master's degree. Was a little disappointed that most of the faculty at the time were not into personal computers because they had order of magnitude or so fewer resources than the bigger mini computers. And so they weren't considered worthy of research. But finally, I was able to make a deal with Professor Fateman that he'd support my Apple II work if I wrote a driver for the VAX that he needed, and which was tangentially related, I would say. And so that ended up being good for both of us. But really, thinking back on it, the most profound thing I learned at Berkeley was TAing, especially for the self-paced introductory programming. I spent a lot of my time one-on-one tutoring these introductory students. By my third year here, Mike Clancy asked me to be the head TA of the self-paced computing. And just sitting there with kids struggling to learn some of the basic things I thought was easy, and seeing how abstraction and complexity were not for most people really influenced my user interface work I did at Apple. It gave me just a sometimes painful first-person experience of how the complexity of computers was the enemy, and helped me really try to make things easier. And so the other thing, I want to thank Berkeley, for this award and for drawing me to the Bay Area and putting me near the epicenter of this revolution as it was happening, as well as helping me have the technical background to make real contributions to the industry. Thank you.
So, let me get this. So our first speaker is Claire Reddy. Yes, it's Claire Tomlin, who's going to speak about safe learning in robotics.
Thank you, Jim. Thank you very much. It's an honor to give this talk, and I want to thank the department for inviting me to give this talk, which should be here somewhere. So the theme of the BEARS Symposium this year is artificial intelligence and machine learning and the excitement around this new vision of autonomy. And I have a background which is, it's not in AI and it's not in machine learning. I'm a control theorist. And in that sense, I work in mathematical modeling and decision theory. And about over the past 10 years, I've been exploring the use of artificial intelligence inside the kind of control and decision structures that I've been working on my whole career. And one of the key points and one of my key motivations for all of my work has been in safety. And that's because I work, and I've worked for a long time in safety critical systems. And I'm going to start my talk today by giving a little introduction to one of the safety critical systems that I've been working on actually for the past 25 years. Let's see if this works. And that's the air traffic control system. So you can imagine this is a safety critical system. This is a system that I would say was never really designed. It evolved. It evolved starting from the design and the use of radar. And so after World War II, there sort of emerged a kind of ad hoc air traffic control system in the Northeast United States around kind of the busy urban areas there. And it slowly built up, and it built up in structure across the country and evolved to the system that we have today. And really, over the past 20, 25 years, there's been some really interesting design questions asked about this system. So it's a system that, as I said, is safety critical, and it's a system that's designed with a lot of margins of error, and buffers for safety. And some of the questions that have been asked and the new technologies that are being designed are automated technologies that try to automate a lot of what the human air traffic controllers are now doing manually. So I have some snapshots here. This is snapshots of data of aircraft traveling for a couple of hours across parts of the Bay Area. So on the left-hand side, this is cross traffic. This is part of the Oakland Center, which controls, well, a huge part of Northern California, as well as a lot of the Pacific Ocean. But here you see traffic on the left-hand side where the traffic, well, you can see it converging on the right plot into San Francisco Airport. So we're only plotting those on the right-hand side, the flights that are coming in. And you can see this structure. And this is a structure that people who haven't really thought about it or studied it are sometimes surprised to see these highways in the sky. So the cross traffic or the high altitude traffic, you can sort of see that. On the right-hand side, you see traffic in these three main trunk routes into San Francisco. And the structure underneath that is quite interesting. So you see some, these kind of pink regions that delineate sectors of airspace. Each of those sectors is controlled by a single human being, an air traffic controller that sits on the ground, watches the traffic from the input into his or her sector to the output, and basically talks to the pilot over radio channels indicating what to do, whether to follow the planned route or to deviate. So I would say the key role of air traffic control is to keep the aircraft separated from each other. Separation assurance is the kind of euphemism for collision avoidance. And so, safety critical system, aircraft have to stay separated if they're away from urban airports. The separation standards are quite big, 1,000-foot vertical and 5 nautical mile lateral separation. And so it's a very interesting control system for those of us who study distributed control, because it's safety critical. It's a human-centered control system. So the human is the critical decision maker here, the air traffic controller, the pilot, they're working together. And so to perhaps manage the complexity of controlling many aircraft at once, air traffic control is rooted on these standard corridors of well-traveled routes. And if we zoom in to look at, stylistically, a merging of two routes into one of the most critical points, or the critical points that air traffic controllers spend a lot of time on, are those points of intersection of these jetways. Those are monitored. Those are the points where conflicts typically are going to occur. And so if you sit behind controllers, and I've spent hours and days sitting behind controllers in different centers and watching what they do, they typically organize aircraft into groups of aircraft, basically by their criticality. So if you have a whole bunch of aircraft traveling along a single route at the same velocity and there's no intersections, that's a fairly simple situation to control, and you can basically group those aircraft together as one, it's like one aircraft. And so if we think about this situation here, there may be three groups. There's one, the blue group, where the aircraft are basically, they're following their velocity, they're simple to control. The most critical group would be the two aircraft that are coming in to the point and have to be, if there is going to be a loss of separation, the air traffic controller will have to guide one or both of the aircraft away. And then they're monitoring the aircraft that are a little bit further out. So we built, one of the early projects that we did was to build a model of an aircraft under air traffic control. And it's, I've represented it in terms of what looks like a finite state machine. There's sort of different modes that a single aircraft could be in. Most of the time it's in that center average speed mode. It's following the velocity that's optimal for the altitude that the aircraft is flying at. And the air traffic controller, if necessary, will try to deviate that aircraft and deviate as little as possible. In fact, air traffic controllers try to touch aircraft as few times as possible. That's that's sort of their mark of a good control system. And so if they can speed it up or slow it down by a little bit, they will, but typically they can't do much without, you don't want to change the speed too much for an aircraft flying at altitude. So they typically have to deviate using things like a detour, a shortcut, a vector for spacing, or as a last resort, put into a holding pattern. And I'm sure many of us have experienced being in those holding patterns over Marin County. That's one of the entry points into the San Francisco TRACON region where they hold aircraft that are coming into land. So simplicity, small sets of control actions, infrequent deviation from nominal, grouping by potential conflict. So when we're thinking about, and I think this is really important, when we're thinking about automating a traditional human-centered system where there is going to be human control persisting for the foreseeable future, that we can't just automate everything. We have to think carefully about how to automate a system so that the people in the loop really understand, and if something goes wrong, they're able to understand and take over. And so it's particularly exciting now. I mean, I've worked in air traffic control, I said, for a long time, but over the past 5 years, it's become very exciting with new types of aircraft and new applications in air traffic control. And one of the things that we've all heard about is the growing use of unmanned air vehicles and how that is impacting the way that we partition airspace and the way that we control these vehicles and what space they're allowed to fly in, and how we design an air traffic control system for those unmanned air vehicles. And we're working, one of the projects we're working on with NASA is called UTM, Unmanned Air System Traffic Management. And a lot of the ideas from air traffic control, it's going to be a much more automated system. These are unmanned aircraft. They have sensory systems on board. So, for example, tactical collision avoidance is probably going to be done in the air. There will be some ground control, but the very short decisions have to be done autonomously. So, but it is a human-in-the-loop system still. So still the concepts of safety are critical. Now safety is not, the key thing for safety with unmanned air systems is that you typically don't want them to fall onto heavily populated areas. So if there's a collision, you'd like a lot of the traffic to be over non-heavily populated areas. Simplicity, because there is a human in the loop. So you'd like to be able to have people understand what the system is doing. And then I think, in terms of moving towards autonomy, the ability to adapt to new information, and that's really where the learning comes in. Okay, so I'm going to talk about two things in the next few minutes. One is safety, and one is this adaptability. And I'll talk about using some of the examples. We have a robotics lab, and we've been building quadrotors now for about 15 years, and now we really, purchase quadrotors and design the control systems for them. But as an experimental test bed, but also as an experimental test bed for this new UTM system. So one of the tools that we've been a proponent of and we've been developing is one for safety critical control systems. And the key idea here is that you'd like to design a control system which recognizes when the system is about to go unsafe and takes an appropriate control action. And you don't want to necessarily, you have to do this all the time, certainly, but for cases where you can't enumerate all possible things that can go wrong, you'd like to be able to design a control system which tries to sort of automatically determine what are the worst case things that could go wrong. And that's what we've been developing. We've been developing a tool, the key idea behind it is this backwards reachable set. If you can characterize what it means to be unsafe for a system, and you can compute in an efficient way ways that the system can become unsafe, not enumerate them, but compute that automatically, then you can design a control system to keep the system out of that set of states that could become unsafe. And so a lot of our algorithmic work in my group over the past 20 years has been characterizing these regions and for different kinds of systems, computing these regions and doing it in a computationally efficient way so we can apply it in real time. And so this is sort of stylistically shown here for a differential equation model, but we've built these for discrete systems, for hybrid systems as well, where you combine that continuous dynamics with a discrete state system. And the kind of concept is nice. If you could take a large state space of the system, a large operating space, and compute the set, you could basically partition the state space into states that are unsafe or could become unsafe, or states that are safe, usually for some finite time horizon that you're evolving the system. And so if you could do that, then you can make some approximations. So over approximations of that would also certify safety for a system. Or the better the model you have, if you have disturbances in the system that you can't characterize well, the more you know about those disturbances, the less conservative this safety controller could be. And that's really important when we start thinking about machine learning in control. Okay, so here's the first example. This is an early example that we did. It's from several years ago now. These are the quadrotors that we actually built. So there are 4 students and 4 quadrotors. Each student is piloting a quadrotor around, and they're trying to crash them into the other quadrotors. But on board the quadrotors is our safety-based control. And you can see the data. Whoa, you can't see the data. Let me try to play that. You can see the data here. I guess you can't. Well, what's being computed on board each quadrotor is its safety-based control with respect to all the other quadrotors. And so those are evolving and changing in real time. And as one quadrotor gets to the boundary of this safety zone with respect to another, the automation on board the quadrotor takes over and it guides the aircraft away, and then it kind of gives control in this experiment back to the student in a fairly random way. It's not the best design for user interface, but it's sort of a design to test out the ability to do this safety control in real time. So if you can do that kind of avoidance, then you can also turn around and design controls to do the typical things you want to do in control. Track some trajectory, reach some target while avoiding an unsafe region. And you can do these for hybrid systems where you can sequence these together as you're switching modes, switching the control mode, like in the air traffic control system. So here's example 2. This is the project that we're working on now with NASA, and we've proposed with them an architecture for UTM, Unmanned Air System Traffic Management, where the control system, it mimics the air traffic control system in that you have a kind of emergent structure of highways in the sky. This would be typically in a separated airspace at a lower altitude airspace from the air traffic control system. But the routes are designed to try to minimize a cost where cost is measuring what's going on below. So heavily populated areas, high cost to fly over. Low populated areas like water, that's a low cost. Airports or the region around airports, that's a very high cost. And so here's a map of the upper part of the North Bay area, a warehouse in Concord that's sending out UAVs to deliver maybe some kind of package delivery to regions in the Upper Bay area. And there's the cost map. And then the red lines are just a simple, it's just a simple path planner to do minimum cost. And what you see emerging are these trunk routes over the cheap areas with short deviations into the high cost areas. So it almost, emerges this highway structure that we've seen in air traffic control that was designed largely for simplicity. But with that, we can think about an architecture for, again, the control system of a single unmanned air vehicle in this UTM system could be modeled as, again, a hybrid system. And we modeled it with platoons. A platoon is a group of vehicles flying along the same trajectory at the same speed. They can be fairly closely spaced. And again, it manages the complexity of collision avoidance. The automated collision avoidance on each vehicle only has to take into account the constraints with the vehicles on either side of it. So you don't have a whole lot of a high-dimensional problem of many aircraft coming into collision together at the same point. A vehicle could either be free, not on these highways. When it joins the highway, it could be part of a platoon, a leader, or a follower. This really, motivation for this came from the 90s when Berkeley was involved in the California Path Project to platoon vehicles at the inner lane, automate the inner lane of California's highways. And then if there's faulty vehicles, they could descend. We're doing this at altitude. So you could, assuming you have the control ability, you could descend and that vehicle could be taken care of. So here, now what do we have to design? We have to design the control laws for each mode, but we have to design the switching control laws. And that's where these kinds of tools for safety analysis come into play. So for example, two vehicles coming onto a highway, you can compute the reachable set, which says this is the set you have to get to, this is the set you have to avoid with respect to the other vehicles, and compute this, and this can be done in real time. And so it's shown here for a couple of vehicles, and you get this kind of, if you do that, there's an underlying controller which is generating the guards of that hybrid system, but you get this kind of organic flow of aircraft merging onto a highway. And you can take care of things like vehicles that are not following the rules. What happens when a vehicle goes right through a highway and it's not communicating? The other vehicles, assuming they have the ability to detect that vehicle, either through their onboard sensors or through ground information, they automatically split from the platoon because their reachable sets touch, and then they join again because they have a goal to get back to the highway. Okay, so third example. Now we're getting into the autonomy on board each vehicle. So this is a system that the FAA has stipulated will have to be on board every unmanned air system in the UTM, is a forced landing system. You have to have the ability to force a landing for a vehicle that's, for some reason, for any reason. And the vehicle has to have some capability to do that autonomously. So NASA, we did this contract with NASA. They were calling it the Captain Sully landing system. So it automatically detects the best place to land, and those best places to land are where there's, not a whole lot of human activity below. And so, here on the Berkeley campus, we were doing some experiments of landing where, again, you want to build this cost map, but not only based on what are the structures below, buildings, trees, pathways, places where you would expect more people, but on real-time sensor data. So you want to be able to learn as you go what are the best places to land and detect and avoid heavily populated areas. So in the last few slides, I'd like to talk about now how we've been taking these safety controllers. So controllers for which, if you trust the models and the limits on the controllability that we've entered into the system, then you can certify safety for these systems, for all possible maneuvers that model can do, and how we integrate machine learning into that. So the ability to stay safe, but also learn dynamic behavior safely, or learn things about the environment. I think I'll skip this one. Okay, so we started by separating the problems. Let's compute a safe region of operation, and when you're inside the safe region of operation, let's learn better models and learn a higher performance control scheme. And so here, this is one of our first examples of this. We had one of our quad rotors in our Vicon lab, and and this is a little bit of a contrived experiment. So the vehicle is, it's a vehicle it's going to follow, or what we want it to do is follow basically a step trajectory, up and down in altitude. So we compute a safe envelope for that. We don't want it to crash into the ceiling or the floor or the sides. So we basically computed a safe envelope that the vehicle has to stay within. But then we took away the model of the vehicle. We took away its model from it. So it doesn't know its model, and it doesn't know the control scheme that it has to follow to be able to achieve this step trajectory. But what it does know is the envelope. So if it hits the boundary of the envelope, it knows what control it has to apply to stay safe. So the first thing that happens is that the vehicle just drops to the ground because it doesn't have a model, it doesn't have a control. But it doesn't crash because the envelope is there, the safety envelope, the reachable set, which tells it that, if you go any further, you're going to hit the ground. And then it kind of bounces up and down for a little while on the bottom of the envelope. And in doing that, so we're running a learning control here, it's learning that as it goes up, it's seeing, well, I applied that little bit of thrust, and that made me go up. So then it knows what it wants to track, and after a minute or two, it learns how to do a good job of tracking that trajectory, but it never violates its envelope. So we've got a safety envelope that we've computed, say from some kind of nominal model, and as long as the vehicle model is some under approximation of that nominal model, it will stay inside the envelope. And so you can do whatever learning scheme you want inside the envelope. So I think that's a first step, but what we really want to be able to do now is learn more about, use the learning. So typically you're not just learning your own dynamics. I mean, that's interesting, but you're also learning about the actions of other vehicles in the environment, about other environmental effects. And you'd like to be able to potentially have a safety envelope that's conservative to begin with, and then as you learn, you'd like to be able to update that envelope, make it less conservative, so that you can fly more high-performance trajectories. So this is just a recap of what this vehicle does. After a while, it does a good job of tracking that dashed blue trajectory. And so what we've got, what we're doing now, and I think I'll skip this video and go straight to the full video, is we're using, we call it online model validation. So we've computed a nominal safety envelope, and then we're collecting data as the vehicle is flying. And if it detects something that says, your disturbance model, your model of uncertainty is wrong, it will contract the envelope, or if it's, it will basically do the action that keeps the system safe. As it learns more and more, if it learns that the disturbance model is too conservative, it will gradually expand that envelope out. So these are two experiments that we ran sequentially, and then I put them side by side. On the left-hand side is, without this learning, and on the right-hand side we have the learning incorporated. And what we've done here is, it's running a bit slowly, but basically we're asking it to follow a step trajectory. And what we've put in here is a big fan in the room. And at a certain point, this is Kene, he comes along and he turns on the fan. And the vehicle didn't have the fan, basically that buffeted air in its model. So when there's no learning, the vehicle will come down. It's not going to update its envelope. Whereas on the right-hand side, as soon as it starts to experience that buffeted air, it recognizes that there's a disturbance in its environment that it hasn't accounted for, and it contracts the envelope. So it won't actually let the vehicle fly in the region where it's measuring disturbances that don't comply with the model that it has. And then what it's doing is it's probing that and basically trying to expand it to make it as least conservative as possible. Okay, so in summary, we've been working on safety critical control systems, and we're very interested in introducing autonomy. So there's all sorts of interesting questions. You're maintaining human in the loop. You have some systems that are human controlled, some are autonomous. How do the autonomous systems manage in an environment where there are some human controlled systems? The human is a big source of uncertainty. It's actually much easier to design a fully autonomous system than it is to design a system that allows human input. And some of these initial flying car models, like the Airbus model, the first representative is fully autonomous, just to take the human out of the loop. So we've worked on safety, and our goal in AI has been to try to introduce learning and data-driven methods in a way that maintain a safety structure. And it's interesting because as you admit that your model wasn't correct and you've learned a new model, there has to be a point at which you say, okay, I trust my new model better, and now I'm gonna evolve over to that. So how to do that correctly is something that we're working on. So the ability to learn from new information. I think there's all sorts of interesting questions. So in a safety critical scenario, that's what I said, how do you update your models? Okay, these are other things that I'm working on. So who owns the data? We're dealing with lots of data. We're using this data. How do we sort of establish this data market properly in learned systems, especially for infrastructures like the air traffic control system, the road transportation system, energy, water, all of these sort of safety critical infrastructures. And I think one of the most interesting problems is how do you model human behavior? It's modeled, in control systems, humans have been modeled very simply traditionally. But we know that we can use learning to characterize perhaps different classes of human interaction with systems. And how do we use that? And how do we use that in the loop to really get high performance, safe control systems? And so we have a number of other projects that we're working on to try to probe these questions. And I think with that, I'd like to conclude and just thank the myriad of students and postdocs who have worked on this and have gone off to other places or are still here in the lab working on these problems. Thank you very much. Yeah, so the air traffic control system, I mean, you can roughly split up between IFR instrument flight rules and VFR visual flight rules. Visual flight rules are, typically flown if you're general aviation. You don't need to file a flight plan. You can basically fly in allocated airspace. Yeah. So In terms of the air traffic control system, we've worked on both. So what NASA is really interested in doing is implementing this automation, so onboard automation, potentially. Right now, they're using the collision avoidance schemes as advisories to air traffic controllers that are, running on their computers in the air traffic control center and doing conflict probes and giving advisories about the best maneuver to take, and then that is transmitted over voice to the pilot. So that could be used in IFR, and then VFR would be a natural area for developing this in a more automated context. As advisories to air traffic controllers that are running on their computers in the air traffic control center and doing conflict probes and giving advisories about the best maneuver to take, and then that is transmitted over voice to the pilot. So that could be,
I think that, the model is to keep the ideas for both, but they would be implemented in different ways.
So if it's VFR, there would be rules of the road, and you'd need to be able to recognize what situation you're in and be able to apply that protocol. And that would be done in the air instead of on the ground and transmitted to the pilot. So with NASA, we're working on both, or we have worked on both. But IFR has actually been more of the focus of this, because they'd like to have a more streamlined way of doing collision avoidance on the ground and transmitting that information. You need to be able to recognize what situation you're in and be able to apply that protocol. And that would be done in the air instead of on the ground and transmitted to the pilot. So with NASA, we're working on both, or we have worked on both. But IFR has actually been more of the focus of this, because they'd like to have a more streamlined way of doing collision avoidance on the ground and transmitting that information.
Position, velocity vector, and so on. How is work going on in incorporating this totally new model?
Yeah, so this is a question about ADS-B, which stands for Automatic Dependent Surveillance Broadcast. This is a protocol by which aircraft would communicate, aircraft in, again, IFR or VFR, would communicate to a region around them information about, well, themselves, but also their, their state, but there's something also about their intent. And yes, so we're working within that model, and it's interesting, right, because it potentially moves, the control, it allows us to think in a more decentralized way, that control can be done on board the aircraft. The challenge is, and this is what we've been working on, often an aircraft is blundering, but it doesn't recognize that it's blundering. It's off route, and it's sending over ADS-B its next few waypoints, but it's not following it due to some error. And so that's the situation they want to protect against. They have a nominal model which may be transmitted by ADS-B, but they want to take into account disturbances or uncertainty into that. So it's interesting because these reachable sets, as soon as you know more, you can shrink them. I mean, the better the model of the disturbance, the less conservative the set becomes. And you can use this kind of as a tool to see how much information do you need so that you have a viable plan. A nominal model which may be transmitted by ADS-B, but they want to take into account disturbances or uncertainty into that.
So I have about 3,000 hours flying a lot of species over in this airspace here in the Bay Area, and 99.9% of the time it works great. And as you point out, the one thing that I've seen a lot of times is because we have a free skies, anybody can go anywhere at any time. Occasionally, a controller in a sector will get smashed because there'll be, I can come in from any direction. I'm typically not going into Oakland or SFO. They've got the Oakland arrivals or the SFO arrivals, and then they'll have 3 or 4 GA guys or couple jets coming off of Hayward or Livermore. And it seems to me the single biggest immediate benefit that your control theory occasionally could supply would be some kind of a warning system that looks out, even if it's 30 seconds, 35 seconds ahead, for an individual sector controller to say, guess what? You've got this sector, and in 45 seconds, you're going to have a whole lot of conflicting traffic. Bozos like me coming in right through your Oakland arrivals or SFO arrivals, and you need to be aware of that. Because every time that I've had something that was a little bit nerve-wracking, it was always the human got overloaded. You know, they can handle a certain number of airplanes and once there's more airplanes than that flying through their sector, they get behind. And then you're kind of on your own when you're flying.
Yeah, I think that's a really interesting point, and I've sat on the other side. I've been sitting behind controllers where not only a similar situation to what you just said happened, but also there's some special use airspace that you know, all of a sudden there'll be a military that have to suddenly change things because they weren't predicting that the special use airspace was going to be closed to civilian traffic. So I think what these kinds of sets or control algorithms do is they give you some predictability. You're basically looking into the future, predicting based on what your current model and your current intent is, and you're trying to measure the uncertainty around that. So I think it's a really good point about we don't want to automate everything. We want to try to we want to understand what should remain under human control and how it should remain. So tools like this should be, they could be used in automation, but they could also be used in advisory. Looking into the future, predicting based on what your current model and your current. Thank you very much. And you're trying to measure the uncertainty around it. So I think it's a really good point about we don't want to automate everything. We want to try to we want to understand what should remain under human control and how it should remain. So tools like this should be, they could be used in automation, but they could also be used in advisory. Looking into the future, predicting based on what your current model and your current. Thank you very much.
Speaker is Professor Peter Abila, who will talk about deep learning for robotics.
We don't want to automate everything. We want to try to we want to understand what should remain under control and how it should remain. So tools like this should be, they could be used in automation, but they could also be used in advisory. Looking into the future, predicting based on what your current model and your current. Thank you very much.
Speaker is Professor Peter Abila, who will talk about deep learning for robotics.
All right. Good morning, everybody. Let me dive right in. So, a lot of my work is motivated by this video over here. What you see here is a video of the Pier 1 robot. And this robot is doing a lot of the chores that we wish robots would be doing for us. But there's a catch. Let me dive right in. And the catch is that Eric Berger, one of the students who built the robot, is sitting inside a harness. And from inside the harness is puppeteering every single motion that robot is making. And this robot is doing a lot of for us computer scientists, this is actually fantastic. What this shows is that the electrical engineering is there, the mechanical engineering is there, and we're just missing the software to make this a reality. And from inside the harness, of course, you might wonder, it's great that this works, but how much would it cost? Computer scientists, maybe it's still expensive. Well, in 2009, the successor of the PR1, the PR2 came out, $400,000. Okay, for research labs, not too great for the home for most people. But then, just 4 years later, the price came down by an order of magnitude for robots that are fairly comparable to the PR2. And so, we're again 4 years later, and so I'm hopeful that another order of magnitude will be shaved off of this, and somebody this year will come up with a $2,000 version. We'll see what happens. But then, just 4 years later, when I got to Berkeley in 2008, the first task we decided to take on was in robots for the home, trying to think about what is it that makes robotics for the home so hard compared to manufacturing. And the big difference is that in manufacturing, you can go through the same motions over and over as a robot and succeed. But in the home, that's not true. And an extreme case of that is organizing laundry. When you organize laundry, even when you're faced with the same set of towels, you'll have to go through a different sequence of motions every single time to be able to succeed. So we started looking at it to see if we can program the PR2 robot to reliably fold a pile of towels placed in front of it. What you see here is actually the PR2 robot doing this autonomously. It's looking at a towel, carefully looking for a corner, finding a neighboring corner, checking if there's a twist line at the top, getting rid of the twist line, and then going to the other table, measuring the size, and then folding. If you paid careful attention, there's a caption at the bottom here. It said autonomous. It also said 200x. This was 200 times sped up. This is great. This was very reliable. Worked 50 out of 50 times. But doing this 50 times took over 1,000 minutes to get this to work. And so if now we had just taken on the next task, it'd probably have taken us 2 years again. It's a very slow process to build up the capabilities that you'd want from a robot like this. And so at the time, we started thinking about what it is that we're really missing to make this easier to program robots. And what we kind of converged on is that we really need more advances in learning. Learning tailored to robotics, such that robots can learn to generalize to new situations, rather than us needing to program all possible situations into the system directly. And the specific type of learning we've been very interested in over the past 7 years is reinforcement learning. And so in reinforcement learning, the way the problem is set up, you have a robot and the environment around the robot, and they're in a current situation. That situation is fed into your agent. Your agent is a computer program, might take in pixels or something. That's how it sees the world. It gets those pixels, then is expected to take an action. What does that mean? Sending current commands to each of the motors of the robot. The robot executes those. Then things change, and your program is faced with a new situation, has to act again, and this repeats. A couple of challenges here. First of all, it's hard to supervise this, because this is a continuous feedback loop. Of course, if you're Eric Berger, you sit inside a harness to puppeteer a robot around. That's one way to do it. But in general, it's really hard to find the time to actually supervise what the action should be at every single time. And so in reinforcement learning, instead of supervising actions directly, the problem is formulated as an optimization of rewards. Reward is associated with the current situation of the world. For example, if your robot is a cooking robot and it brings out a meal, it might have been busy for a half hour in the kitchen, brings out the meal, you eat the meal, and at that point you might say, this was a 5-star meal, 5 points of reward. Comes out again later, another meal, maybe that's not as good a meal, 2 points, 2-point reward. So what you can see happen here is that this supervision is very sparse. It's easier for people to give, but also it's very hard to learn from, because you might be busy for a half hour and get one real number that tells you how good it was what you did over the past half hour. This doesn't just have applications in robotics. Reinforcement learning is relevant anywhere where a system takes an action and then is faced with the consequences of its own actions and has to act again. What are the technical challenges here? Let's contrast this with supervised learning. In supervised learning, you have an input, a corresponding output, a lot of examples of inputs and corresponding outputs, and the machine learning box is supposed to learn the match between input and output. It's a pattern recognition problem. It's always a one-shot thing. You get a pattern, generate the corresponding output if you can. What's new here? Big new challenge is stability. If you make a small mistake, what will actually happen is you'll get up landing in a more difficult situation from which it's even more likely you'll make a small or even slightly bigger mistake, and things can destabilize over time. Credit assignment. That's the problem of the robot cooking for a half hour, and you've given it one number of feedback. You can't learn much from that. It cooks again, give it another one number of feedback. It might now tease apart, what did I do differently between the first time and second time, what might have affected my score, but that's really, really hard to tease apart. That's the credit assignment problem. Third one is exploration. You'd want these systems to do things they've never done before. Because if they already knew what to do, the problem is solved. We're done. You want them to learn, explore, try things, but try things in a clever way so that it's not, so that they can learn as fast as possible about new things, but also in the meantime be safe, just as Professor Tomlin talked about. You don't want to destroy your system while you're learning. There's actually been quite a few successes, despite this being a lot more challenging than supervised learning. Very famous example from December 2013, published in Nature in 2015, and then several related works since, is on the Atari games. The challenge here was, is it possible to build an AI that from its own trial and error can learn to play video games like Atari games? A company called DeepMind succeeded at this first. We've gotten similar results since at Berkeley. They've actually gotten from state-of-the-art results that are extremely similar to our results since. So you go here from pixels on the screen to actions you take with the joystick. Initially, this will not work at all, but the system is supposed to learn from its own experience how to improve what it's doing and over time become a good player. This is able to achieve human-level performance. Here's another example. Can we do this for continuous control? What you see on the right here is a simulator. What you'll see in action is a learning algorithm we developed at Berkeley that is going to change the weights in a big neural net on every iteration, and over time, conversion to a good set of weights to optimize reward. Reward here is the further north, the better. The less impact with the ground, the better. And so what you see here initially, of course, it falls over because the weights are random, it stands no chance. But over time, from its own trial and error, it finds some signal in there, sees the part of that signal, updates the weights, gets better weights, tries again, from that better attempt, gets new signal, and over time improves its control strategy, which in this case is a neural net with about 110,000 parameters, mapping from joint tangles, joint velocities, to torques at each of the motors. There's nothing in there about what walking looks like. It's just trying to optimize how far north it gets and minimize impact with the ground. The beauty here is that this is not specific to two-legged locomotion. This algorithm is general. You can plug in a new robot, like a spider, four-legged spider-like robot, and of course initially it doesn't know what to do. It's random weights again, but over time it figures out how to control this robot from its own trial and error, and actually gets really, really good at making this robot go very, very fast in this simulator. In fact, it's not a bad way to debug your simulators. You'll see that it exploits something in the simulator and is able to go much faster than you'd ever go in the real world, and might be design. Here the reward function is the distance of the head of the robot to standing head height. The closer to standing head height, the better. You see, over time it figures out a strategy to get there. Wonder how long does this take? It takes about 2. We did this in real time. Of course, we can run simulations in parallel. We can run it faster than real time. It takes only a couple of hours in wall clock time. But if you ran it on one robot real time, it would take about 2 weeks per skill. It's also the case that most likely it wouldn't succeed because you run this for 2 weeks, you need to change something in your neural net architecture, change some hyperparameters and go again. But that's how long it would take, assuming you have the right hyperparameters and architecture. Here's another example. On a real robot, collaboration with my colleague Trevor Darrell and Professor Sergey Levin, who just joined us here at Berkeley. What you see here is the PR2 robot learning to place a block into that corner spot. Think of this as learning to insert a key into a keyhole. It's not just about knowing and seeing where the hole is. That's important, but it's also about understanding what it's like to feel out to get things in place. Because just hand-eye coordination is not going to cut it. You need some feel and pushes in place at the right force, the right time. And then, of course, the famous result from last year, DeepMind had AlphaGo defeat the human world champion in Go, a game that many deemed very difficult for AI because of the huge branching factor that is the many possible future scenarios you could encounter, making it impractical to reason for all those scenarios. And what happened there is that deep learning was able to, a deep learning algorithm was able to train a neural net to pattern recognize the quality of a board situation. And once you understand at the end of the game, you can just look ahead a few steps and evaluate the quality of the situation and then decide based on that. There's been a lot of successes, even though this is a hard problem. There's also a lot of challenges ahead. So let me tell you a little bit about some of the challenges that we're looking at right now. First one on the left, multitask and transfer learning. Things I've told you about are all great because the algorithm is very general. You have the algorithm, a new problem, it starts from scratch, learns to do things. It's amazing it can do it from scratch. But it's also sad that it has to do it from scratch. Ideally, once it's learned something, it should use that to learn more quickly whatever the next thing is. That's not happening in any of the examples I've shown to you. And that's going to be critical to build up a wide repertoire of skills. And transfer learning. Faster learning. These things take a long time to learn. And I'll get to that very soon and quantify that. And so we're looking at how to speed up the learning process. But it's also sad. Another thing, even though reinforcement learning is beautiful, it's nice to learn from scratch and invent everything yourself as a robot, it's actually rare that you get very far with just reinforcement learning. Think about all of us in this room. Imagine we had been born in a world where nobody taught us anything. We were learning everything from scratch ourselves. We'd probably not be living the way we're living right now. We'd be living more like the gatherers back 100,000 years ago. It's really hard to invent everything from scratch yourself. It's important also to learn from other people. Safety is critical. Professor Claire Tomlin has highlighted this. On the control side, I'll give you some specifics on the perception side, how to safely build up a perception system. Memory is critical, both in terms of thinking back far enough to understand what happened and to build up on that, also to think about the future. None of you came here thinking about exactly the details of what this room was going to look like. Those details don't matter. But the systems that I've been presenting to you, think about everything at the same level of detail. It's always at the motor command level. It's always at the joystick command level. It's not a good way to reason over long horizons. In fact, it's impossible to reason over long horizons. The last one's value alignment. I suspect Professor Stuart Russell will talk about that this afternoon, but the big question here is, if we succeed, imagine we succeed building an AI, well, what's going to happen? Are their values going to be aligned with our values, or will they not? And ideally they would be, because if they're not, then they're smarter, it's going to be a problem. And then we look at a lot of applications. The beauty of the tools that are currently successful at solving these problems is that they are fairly application agnostic. You can use the same tools for driving, for flight, for manipulation, for locomotion. And that's really, really nice, because now with one line of work, you can affect a lot of application domains. So I'm going to tell you some very concrete recent stories on progress in the three at the top there: fast learning, imitation, and safe learning. It's just a sample of things we've been up to, but just to make it a little more concrete, I decided to talk about three very specific recent pieces of work. They did that. DQN average score 18.9. That's great. The max you can possibly achieve if the other player is not great would be 21.0. But the amount of time it took for this player to learn that was 40 days, whereas for a human, it takes 2 hours. So it's fair to say that the left side is some form of slow learning, and the right side is some form of much faster learning than what's happening on the left. So let's start thinking about how we can address this. Starting observation. The state-of-the-art algorithms in reinforcement learning, A3C, DQN, TRPO, they are fully general. You can throw any situation at them that is some dynamical system and some reward function associated with it, and it is able to deal with that. It might take a long time, but it can handle that kind of situation, and it's not really caring much about what you throw at it. If you look at the real world, the things we encounter are actually a very tiny, tiny subset of the things that are mathematically possible to define as reward functions in dynamical systems. Okay? And so the question is, can we design what we'll call fast reinforcement learning algorithms that actually take advantage of this knowledge, that we only really need to be attuned to a small, tiny, tiny subset of possible problems. So what are the research questions here? First one is how to acquire a good prior for real-world Markov decision processes. That's the mathematical formalization of this kind of setting. So for starters, maybe how to get a good prior for what video games can be like. And then how to design algorithms that take advantage of such a prior to learn more quickly. The key idea here is that we're going to learn this algorithm. Rather than trying to design by hand an algorithm that's good at building priors and then taking advantage of those priors, we're going to forgo our own job in some sense. We're going to say, even building AI, we're going to let the AI do for us, and we're going to have the system learn the fast reinforcement learning algorithm. Okay? Why? Because it's really hard to hand design priors, and it's also really hard to take advantage of those priors and to understand how to do that. So let's see if we can just learn that whole process. So the formulation is you're given a distribution over relevant Markov decision processes, and you're supposed to train a fast algorithm to take advantage of being faced with that distribution to then learn very quickly on a new instance from that distribution. Here's how we'll do it. We'll represent the fast algorithm as a recurrent neural net. Don't get hung up on the fact it's a recurrent neural net, doesn't really matter. Think about it as generic computational fabric that is differentiable such that you can optimize what it computes with some backpropagation. So it can compute pretty much anything, but the weights you put in it will determine what it actually computes, and the learning algorithm will discover the weights, and RNN will encode, the weights will encode the algorithm, and the activations of the hidden units in the RNN will encode what it remembers about things that have happened, that is essentially building up the prior, based on past experience, building up a prior inside there about what typical things look like, and then build up from there. So training-wise, what it looks like, instead of being faced with just one situation, you'll be faced with a first situation many times, and then a second situation many times, and this repeats over and over and over. And you're supposed to be really good at, when you're faced with a new situation again, that is, you're in a new trial, to very quickly learn what that world is like, adapt to it, and do really well over the consequent episodes in that trial. An alternative view of this is that we're doing reinforcement learning, but in a situation where we don't get access of what the world is that we're in. We have only partial observability. We're dropped in a markov decision process. We just don't know which one it is, and we're trying to recover which one it is, because once we can, then we can quickly understand how to act. People have looked at this. Simplest setting in which people have looked at this and have tried to hand design their controllers is in the bandit setting. The situation here is you're faced with a bunch of bandits, and imagine that among these 5 machines, they have different probabilities of paying off when you pull the lever, okay? And so what you're supposed to do is pull the levers on various machines, over time figure out which one seems to pay off the most, and then start focusing on the one that pays off the most. That's the problem, okay? And you can actually mathematically work out an optimal strategy on what you should pull when based on what happened so far. It's called Gittins indices. That's very computationally expensive. There are other ones that approximate it. We're going to compare the performance of Gittins indices with learning a recurrent neural net that invents the algorithm for us. Gittins is over here. Higher numbers is better. Boldface means on that problem as good as the best algorithm that we considered. So Gittins is always among the best. What you see here is RL squared, meaning learning to reinforcement learn matches that in almost all situations. Same thing is true for small markov decision processes where the world consists of just a few states between which you can transition. Again, similar table, there's an optimal way to do this, and RL squared, learning to reinforcement learn, actually matches this. These are tiny examples on which humans have been able to design the optimal way to solve these problems. Of course, that's not where we're interested in applying this. We'll now apply this to situations where humans don't know how to design the optimal approach. So we'll look at maze navigation. So what we'll have here is a robot navigating in a maze, first-person vision. It doesn't have a map, but hopefully it can build a map internally over time if it's smart. But we don't tell it to do that. It just needs to do whatever it is to maximize the reward. So on the left here, you see what the robot sees. This is simulated. And then on the right, you see the map it's acting in. But it doesn't have that map. That's just for our purposes to understand what's going on. All the robot gets is the left, first-person view. That's initially when the RL square is at its beginning. It doesn't know what to do. After having been dropped in many, many, many mazes, it acquires a strategy. What would you hope for? You'd hope that dropped in a new maze, it'd explore, internally build a map, and when it gets a second attempt in the same maze, leverage that map to very quickly navigate to the goal. So let's see if that happens. Dropped in this maze on the right, and again, it doesn't know the map. It explores, checks out different hallways, sees if it can see the goal. The goal is in red. It sees the goal, goes to it, gets dropped again, leverage that past run to right away know where to go. Still a lot of work to do here. Mazes is not the end, but that's where we are at right now for the fast learning. Now let's take a look at imitation. There's a lot of work on imitation learning, actually. It's nice, because you can see what you're supposed to do. It's easier to imitate than to explore everything from scratch. Often, though, it's done in a first-person setting. And that's nice, because in the first-person setting, you puppeteer the robot around. The robot experiences everything the way it's going to experience it when it's autonomous. But there's a problem with that. The problem is that it's not very scalable. It's much easier if the robot can just watch you do things with your own hands. Sorry, I can't read the number. Perfect. The robot can just watch you do things or download YouTube videos and see from a third-person point of view what you're doing and somehow internalize that. So that would look something like this. In a toy example, top row is what the robot sees. Bottom row is the perspective from which the robot will have to execute. So it's not the same viewpoint, and it somehow has to transfer over the essence. There is a recent approach, generative adversarial imitation learning, by Jonathan Ho and simultaneously also by Chelsea Finn here at Berkeley. And what it says is that you're going to represent the reward function, because you don't know the reward, because you're just watching somebody do things and from that infer what they care about. You're going to represent it as a deep neural net, and the way you're going to represent it is by building a classifier that distinguishes the demonstrations from other types of behavior. Now, the tricky part here is that in the third-person view, this doesn't work. Because if you watch from a third-person view and you compare it with your own behavior as a robot, it's always going to look drastically different, and so it's not going to give you the right signal about what's different about the expert from what you are doing. So what we looked at is a technique called domain confusion developed by Eric Tseng, one of Trevor Darrell's students here at Berkeley. And the idea here is that rather than feeding in the raw pixel directly into the system you're learning, bottleneck it through a domain confusion stage, which forces you to go through a stage where you cannot distinguish between two types of information. Here the confusion will be between third-person and first-person view. In that stage, you're not allowed to be able to distinguish whether from those features, whether it's a third-person or first-person view. Of course, at that point, you might erase too much information, not be able to recover what you care about, and so we also give access to temporal sequences rather than just instantaneous snapshots. Here's an example of this in action. So on the left is the video watched by the robot. That's the third-person view. And on the right, you see the robot learning to imitate that. Initially, it's not doing very well. It's still recovering what's different about itself and what it's seeing there, and what doesn't relate to the view, but actually to the essence of the task. But then over time, it figures out what it is that was the essence here, namely reaching that particular ball. This is all from raw pixels to motor torques. It figures out the essence and start matching the behavior. Last little stretch here, let me tell you about safety. So safety is important in a lot of robotic applications, and I think Professor Claire Tallman has motivated this very well. What we're interested in is, can we do this for perception? Okay? Can we learn a control policy that maps directly from raw pixels to controls? So you get in some camera footage, and somehow your policy should say what to do on maybe an autonomous drone. It's going to be some deep neural net doing the computation, because that's convenient to optimize. But we want safety. And so the question is, how do we do reinforcement learning without destroying the system? Only using onboard imagery, no Vicon system, nothing. We just want a drone, put it out there, let it run, and want it to learn to fly, navigate without killing itself, or maybe killing a person or something. So we care about two things. The task cost, we want to achieve something, and collision cost, because collisions is what's going to cause damage to it. And so what we're going to do is we're actually going to build a probability of collision model. For the current image the drone is seeing and sequences of actions it's considering, what is the probability that a certain sequence of actions will lead to a collision? That's what the neural net is going to encode. Then we're going to use that to decide what to do. So we get data. That data is used to build a model that's essentially probability of collision model. Then we use that to choose control, and if we're in a situation where we're pretty much guaranteed collision, we're going to fly slow. You might say, why are we even flying? If you never experience collisions, you don't know when they're going to happen. You actually need to be willing to collide to understand when collision will happen. And then you can backtrace and say, oh, I collided, I saw this 2 seconds ago, so I guess this is a situation in which collision is likely to happen. We use that then to improve our model and repeat. Let's look at some details here. So the cost function we look at is, we don't want the speed to be high, because if we have when, we might get into collision. So if we're high speed, and it's likely we're in collision, and we keep track of uncertainty, and that's key here. Initially, you have no idea whether you'll collide or not. Our neural net will keep track of its own lack of knowledge about what it's seeing. So initially, it'll be uncertain about everything. It'll say, I don't know what I'm looking at, and use that uncertainty to decide to fly slowly. How do you quantify uncertainty? You can use bootstrapping, where you train multiple models in parallel and see on different subsets of the data, see how they agree and not agree. You can use dropout, where you do it in one model, dropping edges, do the same thing at test time, see how they agree. So let's look at a video here of this in action. So first we'll look at what it means to be safely colliding versus unsafely colliding. So this is an unsafe collision. You go too fast and it crashes your drone. that's what we want to avoid. A safe collision would be something like this. You know there's uncertainty, you might have a collision, and it's okay, and now you can learn from that you were seeing something that would likely lead to a collision. This is what our training looks like. There's no Vicon system, no motion capture, nothing. This is just a drone on its own in an environment with obstacles. On the left is naive training. On the right is the safe training. And what you see on the top is a histogram of the speeds at which collisions are happening. And you'd want that collision to happen at low speeds. So what you want to see here is that on the left, the collisions are happening even at high speeds, which is not great, that's unsafe. Whereas on the right, it's rare that a collision happens at high speed, which means the drone understood when to not go fast and slow down, and then learn from that collision to build a visual understanding of the world and where collisions might be. And so you see that indeed it learns a lot more safely than when trained in the unsafe way. Last little video here. What you'll see here is the NASA Tensegrity robot Super Bowl. This is a robot that's meant for space exploration. You can compress this down to a plane. It's a bunch of rods and cables. You pull the cables, shorten their length, center of gravity shifts, robots rolls over. This has been very hard to control. Our reinforcement learning approach is the first one to be able to reliably roll this robot over, in this case, flat terrain, and this wasn't possible until a few months ago. All right, here's what actually, before I wrap up, if you want to try this yourself, our lab has all the code that I talked about. You have a friend who wants to try it, all available, MIT license for any kind of use you might have, a commercial, non-commercial, up for grabs, or contributing back if you can. Here's what I talked about. We also have a lot of other things going on that I didn't talk about, but thank you for your attention, and if you look for any collaborations, feel free to email me. Thanks.
Robots, or can a robot like learn from other robots, and it can be in a friendly environment situation, or it can be adversary environment?
So, very interesting. How can robots learn from other robots? We have some work on that. For example, we have some robots that are running 24/7, that are sitting in a basement, and they're just pushing objects around, interpreting what's happening, trying to get better at pushing them around in ways that they want to understand and control them to get into certain configurations. And so the more of those you have, they can share all their data. It's essentially trivial to learn from each other because they can just share all their data if the robots are essentially the same, and that speeds up learning a lot. Some other ways robots can learn from each other, if they're not the same, you'll have to do more careful adaptation of what it is that they're learning. For manipulation, a lot of the challenges are in interaction of objects rather than the robot. The robot is relatively simple compared to what the objects are that you're manipulating, so transfer, again, shouldn't be too hard across robots. Unless you have very dynamic tasks like throwing things or hammering things and so forth. Another way robots have learned from each other, for example, a project by some colleagues at CMU, is where a robot does something and then another robot comes in and perturbs it to make the task harder. And so it's very interesting to see if you can make tasks harder by bringing in adversaries and that way gradually build up skills. And robots can do that also to themselves. You can imagine you introduce noise on the execution. And actually, a lot of the learning that happens in what I showed to you, there is noise in the execution explicitly in there, such that it's trained to learn a more robust strategy than if it had full control over what it's doing. In general, the more robots, the more data, the better this is going to work. Thanks.
So our next speaker will be Dan Klein doing conversational AI.
apologize. I'm lost in connectors here. Is there, I have a flash drive if there's a laptop? Because there isn't a proper HDMI connector here. Is the thing. So I was told bring an HDMI connector. That's what that is.
Yeah, so you don't have a,
That is a mini HDMI.
yeah. And you don't have VGA?
Nope. I do have a.
Okay, connectivity problem. Let's see. Is there a way to get HDMI?
Somebody else I have. I also have this on a thumb drive if somebody else has a computer.
I have. Let me get my computer.
It's possible my talk on conversational AI will have to be conversational. No, I need either mini or. So I have like a mini HDMI, and I have a regular HDMI, which is what I thought I was told to bring.
Let's just do that.
Can you? It's PowerPoint. Sorry about that. Oh, it's okay. I would have brought that. I thought I brought what I was told. It's USB.
Oh, there it is. I was looking for it.
Do you think that could make it up onto the podium? Lifesaver, thank you so much.
So plug it in? No, we're there.
We've worked around it.
Well, okay. I think they might have gotten it. This is a,
What's on the other side? That would have worked, but I think we're ready to go.
okay, thank you.
Magic.
All right. Thank you for your patience. I'm Dan Klein. I'm going to talk to you about conversational AI today. This talk is going to include joint work with my colleagues Jacob Andreas, Marcus Rohrbach, and Trevor Darrell. It also includes a few slides and maybe some perspective from my other life at Semantic Machines. So looking back over the past few decades, there's been an evolution of the kinds of natural language systems we can build. The first things we could kind of really do a great job at were systems that were about finding language. And that's things like search or information retrieval that were able to get you what you need without really interacting with text beyond kind of the presence or absence of words, at least in their simplest form. The next iteration of this was systems that were about transforming language. And here I'm thinking about things like speech recognition and machine translation, where suddenly you had to actually grapple with the structure of the language in order to transform it from one form to another, whether that was sound to text or one language to another. But you didn't necessarily need to know what it meant. You just needed kind of really rich models of correspondence and structure. And the stage that by and large we're at today is systems that are starting to actually understand language. So these are systems for question answering. For example, a very public and cool example of this was IBM's Jeopardy system, Watson. Or command systems like something like Apple's Siri or Amazon Alexa, which are able to take natural language instructions and then execute them. In order to do these things, you need to not just know about the structure of the language, you need to know something now about how it connects to other things. The next iteration, and what we're on the cusp of now that I think is extremely exciting, and what's coming, is conversational language systems. These are systems that rather than just taking language and producing an output, instead they do things interactively. This is things like dialogue systems, conversational systems, interactive systems, and really the hallmark of these systems is rather than executing your commands, they interact with you to solve problems. And I think this is going to be transformational. And you're already starting to see both the first initial steps in technology and also the demand from the world. So if you think about things like Microsoft's Cortana, Google Now, Apple's Siri, Amazon's Alexa, people want to use these things. People think they're awesome. So Siri gets billions of queries a week. Amazon Echo is selling like hotcakes. And these things are really exciting, but they're really just first steps. These aren't yet conversational AIs. They're systems which take natural language commands. And one of the things I'm going to do today is talk to you a little bit about what the differences are. What are the things we still have to do and still have to invent to get to true conversational systems? And then I'll go a little bit into depth on just one project that we're working on here that addresses some of these issues. So what are future conversational AIs going to do? What are the hallmarks of these things? Well, like I said before, one of the main ones is that a true conversational AI will not just take commands, it'll solve problems. So to have a true dialogue with the system, as opposed to a command and control system, requires a second intelligence. It requires that you're able to express your goals and to interactively achieve them with the system. This is the difference between talking to a travel agent where you say what you want and you work to get it, versus going to a kind of online web booking where you need to know your dates and select drop-downs, right? Conversational AIs are also importantly going to act. That means technically they're going to be grounded systems. So if you say, hey, can you order me a pizza? It's not enough for the systems to say, done, it'll arrive at 6 p.m. Because, for example, it's heard that's how you reply to can you order me a pizza, right? You have to actually order the pizza. It has to actually show up. You can't just say things that seem plausible. They have to actually anchor to the world. They have to actually charge your credit card and show up in a car 30 minutes later or whatever it is. And in order to act, a system has to be grounded outside language. And this is a key piece of what we mean in these current systems when we say they understand something. They connect language, which is the symbolic thing, to actual actuation or perception in the real world. And that connection is something we're just really starting to master now. The next thing that conversational AIs are going to do is they're going to contextualize very heavily. And there's a lot of kinds of context. So for example, let's say you're talking to that travel agent and you say, hey, can I get there earlier? Humans say things like this all the time. It's actually really annoying for people who work on natural language. Humans underspecify, which means they leave out all the details. Can I get there earlier? Where's there? What does get there mean? Earlier than what? And because of this, in order to interpret things, you need to interpret them in a context. And in this case, this example requires a lot of linguistic and task context. But there's other kinds of context too, like personalization and goal and task achievement. The last thing that conversational AIs are going to do is that they're going to connect things up. And I think this is actually really, really important. So I might want to say to my conversational assistant something like, get us 2 movie tickets, make reservations at the Italian place by the theater, and call us a ride there. Well, in order to do this, I need to have the system know about a bunch of different domains, but that's not enough. It also needs to be able to connect them together. And this has ramifications both for what these systems will do for us in the world, and also the technologies that it's going to take in order to actually build them. The power of a dialogue system, of a conversational system, is really not in finding information. Search is already great at finding information. It's in connecting and coordinating information and taking action. And in order for systems to do this, they have to be multi-purpose. You have to know about movie tickets. You have to know about kind of where the theater is and which places are Italian places, and connect them all up and sequence these things. And in order to connect all of these domains, it's not enough to know about the domains, but you have to reason about how they interact. So you've seen a lot of deep learning today. I'm going to tell you more deep learning. And so you might look at these problems and say, okay, those are some capacities we want to build. What are the challenges and what are the solutions? Certainly a piece of the answer is deep learning, and that's been very powerful. There have been a lot of success stories, many of which you've seen today. So Peter talked about game playing. There's been really huge advances in computer vision and speech recognition from these deep learning methods. But there's a little bit of spice we still need in that stew in order for it to work for natural language and for these kinds of conversational systems. And mainly it boils down to one limitation, which Peter also alluded to, which is that the way we build deep learning systems today, they're very data hungry. So they require a whole bunch of data in the form of, in this context do this, in this context do this. Okay, and they require a lot of data, or in the reinforcement learning case, a lot of experience. And when you give them that data, they then do one thing. So what does that mean? It means in order to build a system that does lots of things, I need a lot of data a lot of times. And even in this data-rich world, that eventually becomes expensive and maybe even impossible. So the main limitations of these systems is they require a lot of data to do one thing. The main solution, in our view, is that when you add structure to these systems, it lets you build a single system which can do lots of things in a kind of very sample-efficient way, meaning it leverages the data it has to learn to mix and match a lot of different functionalities. And I'll show you one example of how we might do that today. Okay, so that was a little bit of an overview of the kinds of things that are coming, the kinds of technologies that we're really kind of now able to build, and the kinds of challenges that we're going to face in building them. I'm going to talk today about one piece of the work we're doing here that connects to some of these things. I wish I had time to talk about more. I'm just going to really overview one. What I'm going to talk to you about is a class of models that we're developing called neural module networks. And this is going to touch on a couple of these issues I mentioned. One of the issues is how to build language that actually grounds into, in this case, mostly perception. And it's also going to touch on how to build systems that are able to connect lots of things and mix and match. So the kind of data these systems that we've applied them to and where they were designed were for systems like grounded language, grounded question answering. So for example, in the visual question answering task, you take an image like this, paired with a question like what color is the necktie, and you're supposed to say it's yellow. Now this is close to what computer vision does, right? Computer vision is really, really amazing at finding necktie detectors. But there's a difference between a necktie detector and a what color is the necktie answering system. And that's like a little too specific to gather tons of data for just this one question. So we want to be able to answer these questions in a kind of on-the-fly way. Another example in a different domain is in answering questions that are grounded not in perception, but of, say, a natural image, but in a database. For example, what rivers are in South Carolina? You ask that out of a database, and then there's some answer that's appropriate for that database. So it's another kind of data I'm going to show. And the third one is a synthetic data set that I'm going to talk about for kind of exposition purposes today, called the shapes data set, where the interactions are actually much more structured and rich, but the images are pretty simple. So you say things like, is there a red shape above a circle? And you're supposed to say, look at this image and then say yes. So how are we going to do this? Well, we have pieces of this already. So in order to understand an utterance like this in a context, we need grounding. So you're not going to be able to answer, is there a red shape above a circle, if you don't know what a circle is. So how are we going to figure out circles? Well, now this is the kind of thing we already have good machinery for. Computer vision is really good at building detectors. Neural nets are really good at mapping percepts to features that would let you do this. So neural nets might give us a way to attack circle detection, but that's not enough. There's a separate tradition in the natural language processing community called semantic parsing, which is really all about compositional structure. So in order to do this, you can't just know about circles. You need to know what is the region above a circle. What are the red shapes? How do they interact? What question is being asked? And that involves taking all of the pieces and putting them together in a compositional way. But typically that's not done in a kind of directly grounded context. So you would kind of have the techniques for combination, but not necessarily the network grounding. And so this work I'm going to talk to you about now is about doing both at the same time. And the basic idea is we're going to take little modules of neural networks that we learn them kind of all together, but we learn them in a way that they can be mixed and matched on the fly. So for example, here, in this shape, in this image, if we want to say, is there a red shape above the circle, we think, how is this going to happen? What does this even mean? Well, the meaning in this case is kind of a structured computation. So when I say, is there a red shape above the circle, well, the red detector is going to have to do its thing. The circle detector is going to have to do its thing. The circle detector is going to compute where the circles are. The above module is going to map that to the regions above them. The and module is going to do some kind of logical combination. The existence module is going to figure out how to answer that question and how to render that into language. So that structured computation both takes these little grounded modules, which we're going to realize as neural nets, and it also assembles them in an ad hoc way. So the flow of this is going to be you have a collection of modules that you've trained. And you don't train them one by one, you train them all together. I'm not going to get into that today, but you have a collection of these modules that represent little pieces of meaning. And each one is backed by a neural network that grounds it, that tells you what that actually means. And then in comes a new question that you've never seen before. Is there a red shape above a circle? And what you're going to do is you're going to build a new network out of these building blocks, just like Legos. They're all designed to be interoperable when you learn them, so their latent variables are all kind of interchangeable. And you build them, and now what I have is I have a network. This is a single-purpose network. This network only answers this question. But I didn't have to train it. I built it out of other pieces that were learned from answering other questions that had structure in common. So you apply that to the image, it gives you an answer just like a single purpose network. This network just didn't exist until just a second ago. So what are these pieces? These pieces are little fragments of neural nets that can be recombined. You can think of little circuit chunks. So for example, one kind of module we have are the detection modules. These tend to be the groundings for things like nouns and adjectives. We call them find modules. This is for things like red or necktie, or whatever's appropriate to that. And they scan over the input, whether that's an image or a database, and they light up where there's, here where there's red things, but they don't light up where there's not red things. And for example, when you do this with a necktie find module, it glows where the neckties are. And if you do this in the database settings with the detector module for town, it glows for the things that appear to be towns based on the context. So it's all one kind of module, but in different domains, it's going to learn to ground in different ways. Of course, you're going to need other kinds of modules. You can't just detect things. There's going to be description modules. This is what takes a glowing region of an image and decides how to render that in natural language. This is almost a little mini captioning module. And then there's going to be logical connectives, and there's a set of these that you need in order to be able to build the whole range of functionality. Of course, you need more than modules. You need to be able to compose them. How are we going to compose the network for is there a red shape above the circle? Well, the good news is the natural language is more or less a blueprint for answering the question. So we can take this, we can do a syntactic analysis of it, and then we can look at that and say, you know what? The syntactic structure here, it may not be exactly the blueprint for the network, but it's pretty close. So we learn a mapping from that to how the blocks go together. There's actually another neural net that's reinforcement learned that learns to do this, but I won't get into that now. In any case, basically the language turns into a network topology, which is then populated by these modules, and then you point it at images. So to give you an example, here's another question. This is an actual question from the VQA dataset. What's in the sheep's ear? And it may be kind of hard to see. There's a tag in the sheep's ear, and the system looks at this question. It realizes we need the sheep module, we need the ear module. We're going to have to conjoin them, and then we're going to have to describe the result. And that network produces the answer tag on this input. Okay, it does that by first combining sheep and ear to glow the right region, and then the description module comes in, and these things more or less kind of march along the computational structure. So how does this work? It works. So in the VQA dataset, which is actually not very compositional, they're fairly flat questions, it still gives you a gain over systems. Of course, it's also very important how good your underlying vision is, so these numbers have been marching along, but you do get a gain from this compositionality. In the GeoQA dataset, which is a little more compositional because it's backed by a database and you have to variously join things and do other database operations, you also get a gain over state-of-the-art systems, which are compositional. Here you're getting gains from more the neural machinery. And then in the shapes dataset I've been showing you, the gains are actually huge. This is a dataset where it's very compositional and it's very hard for other techniques to use because you basically can't answer these queries without actually relating one thing to another and kind of doing things right from the bottom up. And here, almost all the errors go away when you deploy this kind of modular architecture. Okay, so what is this I've talked about? This is neural module networks. And what's really going on here is that the linguistic structure of the example more or less dynamically generates the structure of a network that you didn't have before, but you'd like to have now. And then you take all the pieces that you have recycled from other examples, and you stitch them together in a new way. And now you have the advantages of a neural net where you've learned the representations, but because you learn them in a way that they have to be able to mix and match, you also have the advantages of compositionality like semantic parsing, so that these networks can recombine to do new things which are not exactly the things they were trained for. And this is one way where you can allow one model to contextually do many different kinds of things. It's certainly not the only kind of structure. It's not the only kind of context. There are others. For example, if you have, in another project that we're working on, if you want to take a scene and describe it, that's a captioning problem. Okay, that's a fairly standard thing that people work on in the kind of the vision plus language community. But if you had two images and you wanted to differentially caption them, you say, tell me something that causes a user to pick this image and not that one, suddenly the right thing to say depends on the distractors and it becomes a pragmatic task. That's a different kind of structure that you can use similar techniques to this in order to give you contextual answers rather than having a system which only does more or less one thing determined only by the input. It can also be determined by context and structure. So I would love to go through a bunch more of these things, but instead I'm going to come back to the question I started with, which was, what will future conversational AIs do? And I listed some properties. So unlike kind of command and control systems, you're going to be able to go back and forth with them. You're going to be able to do problem solving. What does that mean? That means there's going to have to be inferences over your goals and the actions the system should take. You're going to be able to do things that are grounded. That means things are actually going to connect to variously databases, perception, action, just like the kinds of things that we saw earlier in this talk. You're going to be able to contextualize things, which shows up in various different kinds of ways. And when you have a system like this, I think it's going to be a very different experience, because the more you contextualize things, the more you can connect multiple different domains, the more things basically come down to the devices you have and the kind of physical world around you and the things that you can do and the services and the goals you express, and in many cases that may be through natural language. And the intermediate layers kind of fade a little bit into the background. And I think that's pretty cool. And I'm really excited to see what things look like as we start taking steps as a community towards that. I think my expectation is that conversational AIs really are going to change the way we interact with our devices, services, and they're going to change the way we use the internet, right? Because a lot of these intermediate levels will go away. That's all I have for you, but I would be delighted to take questions. So thank you. What do I think about using a GAN to generate conversation? Yeah, so it's so a very cool question. So for those people who don't know, GANs are basically a learning paradigm where you think not just about here's an input and here's the right answer, but you think about there being an adversary that's sort of forcing you to learn the right thing. I think it's a powerful idea, but I do want to point out one kind of key thing as the core of my answer, which is that dialogues are cooperative. And so when you think about things like that, you really need to think about the fact that when you are talking to somebody, they're not an adversary. In fact, when you talk about coordination games, when you talk about having multiple agents, this is another line of work that there's a couple instances of happening here at Berkeley, agents inventing communication protocols. Those protocols only really make sense when there's at least an element of cooperation in the game. If you have kind of something entirely adversarial, which I understand is not the only aspect to your question, a lot of that goes away. So you need to just make sure that the part you have adversarial is really the kind of distractor effect rather than the actual structure of the dialogue. Yeah, I mean, yeah, absolutely. Like I said, it's a powerful idea. This does get into issues of like, what does it mean for a dialogue to be correct, right? There are alternate dialogues which also succeed, and so this is it's a complex issue, but I think the idea is a good one. Sure, yeah, if any of you would like to talk to me, please come do so. I'm gonna keep answering questions until they tell me to stop. They haven't cut me off yet. Any other questions? Okay.
Before lunch, I have an important announcement. A red Kia Sorento in the parking lot next door is about to be towed. So if it's yours, please move it. So, yes, it obviously needs automatic driving to avoid that, doesn't it? So our last speaker before lunch is Michel Maharbiz, who will speak about recent advances in neural dust, a platform for peripheral and central nervous system recording.
All right, I'm keeping you from lunch, which is horrible. So I will try to balance speaking quickly, but actually giving you some information. Hopefully this is a pretty straightforward story at 20,000 feet. And then I would say that if the details or the application matter to you, please contact me. You can Google my last name at berkeley.edu, and you can email me. I also want to add that we think that what I'm about to present is a pretty powerful platform, and as you'll see, I'm going to build a story that has to do with a particular application, and then in the very last slide, I'm going to pull out on the table and say, oh, actually, we can use it for a lot of these other things. We are setting up at the moment, Berkeley is setting up, working to set up an entity to handle the IP related to this because we think and we know there's quite a lot of interest in using it. Okay, so having said all that, I also want to add that this has been a wonderful collaboration. It's the product of work out of my lab, Jose Carmena's lab, who I'm sure many of you have seen before speaking here on brain-machine interfaces, and as you'll also see in the first few slides, I sort of harken back to some of the themes that he has really been pushing at Cal for some time. Elad Alon and Jan Rabai, who are legendary circuit designers, and increasingly Ricky Muller and others who I'll mention at the end. And so it's a big family EECS effort to pull this off. All right, so before I tell you what Neural Dust is, I'm going to give you two application spaces that are very different, sort of two different motivations for doing this. The first is sort of far out, and the second is really starting to ask a more specific medical question. So the far out issue is that the way we interact with our increasingly complex, sophisticated, ubiquitous, all those wonderful words that we like to tag on to articles, as we do this, we actually have a fairly low bandwidth connection to our devices. And you know, people are constantly trying to find new ways of doing this, but the reality is that we order reduce from an extremely complex thing here to another extremely complex thing, but the sort of channel between them is very limited. So just keep that in mind. It's something that's driven sort of the blue sky view of a lot of things. We would love, in some fantasy universe, which I will convince you we are beginning to chip away at, we would love to get rid of that low bandwidth keyboards and touchscreens and so on. Okay, now a less blue sky thing that motivates us, our application, is in the medical space. And here I want to point to two versions of this that have been in the media a lot, that are driving a lot of science, a lot of engineering in this country and around the world. Let me start with the one on the left. The idea of a brain-machine interface, the idea that taking signals from the nervous system and using them, running them through synthetic control systems and using them to run prosthetics and other types of assistive devices, if you will, has gained a lot of traction over the last decade. And it's increasingly the case that we are moving to a world where we can help and we can address many sort of clinical needs using this kind of paradigm, using this. And I'll talk a little bit more about that. At the same time, there has been, I would call it a gold rush over the last 3 years, 4 years, to address the needs of the periphery. So this story has largely, incorrectly, but largely been cast as a central nervous system issue. There's your brain and it's going to run things. This has been cast as a sort of all of the maladies of the peripheral nervous system. And it's driven because the peripheral nervous system is more accessible than your brain, for obvious reasons, right? And it's been observed by commercial actors and by academics that there is a lot that could be done to address clinical needs if one understood and had the technology to take data in and out of peripheral nerves, because they absolutely, you know, I would say control everything is sort of a glib thing, but that's what they're doing. They're really at the heart of everything that goes on, even to the point of amazing research over the last decade by people like Kevin Tracy in the Feinstein Institute in New York, who's shown how tightly coupled our peripheral nervous system is to immune response, which is a really big deal if you start thinking about it. So this is driving us. Okay, but what happens? So now let's get down to the nitty-gritty. At the heart of all of this, there has to be some technology that couples to the nervous system, whether the brain or the periphery. There has to be something that is taking the data in and out. And it has to be for these applications, clinically relevant. It has to be, you have to be able to put it into people. It has to last, and we'll talk about that in a minute. These are examples of the now classic pioneering trials that were done in brain-machine interfaces. So here you see those little red squares I just turned on show you where a craniotomy has been performed and a system has been attached to the skull, and within that system, part of that system, is a tiny millimeter scale array of effectively needles that are pushed into the cortex. And those have electrodes on them, and they're used to electrically record neural signals. And this is, from the perspective of human approval, this is the state of the art. And the things that were demonstrated were rather remarkable. However, from a technological perspective, there's a lot to be desired. And so what I want to show you as a sort of prelude to the story is what it looks like today. And what it looks like today in approved devices, what I just showed you, but of course, research and development is always ahead of the curve of approval, and so I'll give you a taste of what that looks like in that realm, and then jump forward to what we have demonstrated. So I'm not going to, this is a very loaded, beautiful chart here, which actually should have attribution to paper by Schwartz in 2006, but it shows you the many different ways in which one could try to take data from the brain. And we don't need to really delve into this too much because we're limited time, but the bottom line is people build grids and arrays of electrodes, and they put them onto or into the cortex in the case of central nervous system interventions, and they record data. They record the firing of neurons or the lower frequency effects of many neurons firing, which don't look like little spikes, they just sort of look like waves at certain frequencies. And this data is then used to inform some sort of intervention like what I showed you with the robots. We're using a BMI, or perhaps taking data off of, for example, say the state of a Parkinsonian patient's brain state and how that relates to, say, drug dosing, something like that. So this is what it looks like. And these systems are made by a variety of different technologies. They're all very small, and the intent is, of course, to harm the least amount of tissue. Having said that, the current state of the art today, to go back to that original theme, is that we have hundreds, soon thousands, in terms of a very robust technology of recording channels, but you can see that on both ends of that, both the electronics and the brain, is much, much higher parameter space. So this is a quest the quest to increase this is something that's motivating a lot of people across the country. Okay, so what do you need when you build these kind of technologies, whether it's going to go up into your head or it's going to go onto the peripheral nerve? Very quickly, you need to be able to see the signal that you want, obviously. Many cases, you want to stimulate back. You want to be able to adjust the nerve function. You want to process the stuff you're getting out, often locally before you send it out. You need power to power all this, and you need to communicate with all of this. And you really are constrained by the fact that all this is going into biology. And now as we narrow, what I want you to keep in mind is that I'm going to make a very specific statement that you can go and vet. We do not have technologies today that will last for an appreciable fraction of a healthy adult's lifetime once implanted for neural recording. It's just true. It is absolutely true that I cannot guarantee if I put something in there it's going to neural record, peripherally or otherwise, that it's going to do its job for the next 40, 50 years if you're relatively healthy. And of course, it's been less relevant because usually these technologies have been so risky that they've been used in very sick patients, to be very honest. But this is an issue that is now emerging. How do we make chronic, how do we get things to last? How do we make things that really, where the bar is lowered in terms of risk? And the problem there is very, very complex. And there's a whole literature on this. It has a lot to do with the fact that you're building solid-state physical systems that then have to survive in what is effectively an aggressive aqueous environment. If I told most of you, take your phone or a chip, if you're a chip maker, throw it into the ocean, and it's got to still be operating in 30 years, most of you would be like, that's absurd, like most of us understand. But for some reason, that was not as intuitive. Well, the same thing as your bag of salt water. It's the same problem. And it's worse, because you have active biology that's attacking these materials. On the other hand, your system can damage the central nervous system due to size, right, if it's huge, due to tethered effects. If there's a wire connected to this, which is almost all of them, it's going to sit there in micro motion. And so you then get a response by the body. It's a very complex issue in both directions, what harm you do to the body and what harm the body does to your object. We believe that one of the, and it's backed by data, which of course I'm glossing over, but one of the key needs is to make extremely small being like a fraction of a human hair eventually, extremely small implants which are fully tetherless. So you put them in, close everything up, and it's just sitting there. There are no wires, there's no large object. That was the quest that motivated what I'm about to show you. So today, at Cal, we've been pioneering this. Jan Rabai and Jose, years ago, began really building the critical mass to do this. And there are many firsts that have continuously been coming out of here. And what you see is, if you look at what these systems look like, right, that are going to take this recording and attempt to send it out, say wirelessly with an electromagnetic signal, an antenna, or a near-field coupling device, or whatever, you do run into some basic constraints that are set to you by these circuits, which is that usually, you need about a square millimeter per channel of area of active electronics. You need about a microwatt per channel. I mean, these are all rough numbers, but these are good to keep in the back of your head as I show you what I'm about to show you. And people have moved to build these things tetherlessly here and elsewhere, but all of these systems classically relied on electromagnetics. Let's build an antenna. Let's get this thing and put it in there. It'll have an antenna. We can talk to it. This doesn't work, or at the scales I'm proposing, to be exactly clear, won't work. So let me explain why, and then let me show you what the only slide you have to remember about this whole talk, okay? Not this one. It's coming. And then I'll move quickly so that you can all have lunch. So if I'm building a very tiny thing putting into the body, that's going to be that little coil that says RX. That's however you want to build it, okay? Whatever antenna design makes you happy. And you are going to put that in the body, and then you're going to optimize some external transceiver, and you want to use electromagnetics to couple this. Whether it's near field or you do far field, the argument is going to hold. You have a problem. The problem is twofold. You have two problems. The first is that light is very fast. If light is very fast, the wavelengths associated with the electromagnetic field are going to be large, and so the size of the object, all other things being equal, is going to be large. Even for very high frequencies, even like tens of gigahertz, they're very large objects that you need to properly couple. Even if you play tricks, and there's all sorts of awesome things that are done, it's just a true statement. The other problem is that you're a bag of water, and electromagnetic fields like to make the ions in the water in the bag of water oscillate, which means it's loss. So you're dumping energy. Electromagnetic fields do not penetrate easily into salty bags of water. So what happens is, if you take all this into account and build a nice model, you look at, as the implant, on the x-axis, the implant is a centimeter, then a millimeter, then 100 microns in size, and you ask yourself, how efficient is my ability to put power or data in? You find that it's great for about a centimeter, which is classically what everybody's done very well, and then you start to get to a couple of millimeters, then you get to a millimeter, then you get smaller, and that's a log scale on the left. It is very hard to couple using electromagnetics into 100 micron objects. And if you do the math, quick example, 100 micron object 2 millimeters away from an interrogator, you get picowatts. Very, very small amounts of power. What does work? And this is the slide you have to remember. You can look up from your email, and then I'll keep going. I was just in the audience. I know what it is to be in the audience. So just look up from your email for 30 seconds. All right. So what does work is this, ultrasound. What you do is very simple, actually, to explain, and it works remarkably well. You build an implant that has a piezoelectric crystal in it, and that crystal is going to mechanically resonate or oscillate at a particular frequency. Okay? You then, from outside, launch an ultrasonic wave at that frequency. This is not electromagnetics, it's pure ultrasound. Ultrasound goes through the body wonderfully. You all know this because you all get ultrasound scans, or significant others do. Goes in, bounces back from this crystal. Now, several things happen. Well, first of all, there's energy bounce back, right? What else happens? Well, the first thing that happens is, because it's a piezoelectric crystal, as it's hit with mechanical energy, it will transduce that to electrical energy. So I can use the crystal to power something. The second thing I can do is, if that thing that is being powered can change the total impedance of the crystal with respect to everything else, the amount of energy reflected will change. Those are the two key concepts. I send an ultrasound, and I adjust whatever is being powered. I use that thing to change how much is being reflected back. So there's no onboard power supply. It's backscattered, just like your RFID cards on the subway, but it's done entirely with ultrasound. And now the trick is, can I put something on that crystal, some circuit connected to it, that as a function of neural firing events will do that modulation I just described? If you can do that, you can put this tiny object into the body, close everything up, and interrogate it with ultrasound, and it will report back how neurons are fired. And many other things, as I'll show you in the end. That's the story. Now, of course, how would we envision doing this? In peripheral nerves, you imagine putting these little things into nerves. In the central nervous system, you imagine putting this, what we call neural dust, into the cortical structure, and then having ultrasound interrogators talk to it. Okay? Now, because I want to be brief, you can imagine that what I just said has papers worth of math behind it, and you can go look at them up. There will be referenced. Actually, some of them are referenced right there on the bottom. But the key is that if you actually look at the math, ultrasound is just a orders of magnitude better way of doing all of this than electromagnetics, and it opens an entire new frontier in building small implantable devices of minimally invasive devices that do all sorts of crazy things. So I want to show you one crazy thing, and then I'll show you all the crazy things that are like blooming, and I'll be done. So to demonstrate that this was true, we built such a system with commercial off-the-shelf parts. We wanted to show that almost anybody could put this together relatively quickly and build a 1 millimeter implant, put it into a nerve, and do this. So that's what you see here. That's a 1 millimeter. Back when we published this paper in Neuron, which is the bottom reference, this thing was 2 millimeters by 800 microns. By 800 microns today, it's 1 by 1 by 1, and it's just getting smaller, more or less on its own. But anyway, so that's how big these things are. You can see the piezo and the little circuit, the recording electrodes on the bottom, because we're going to take an electrical recording of the nerve. This is implanted on the nerve, and there you see, at the time, what was our little FPGA board that ran the external transducer, and it used a chip, a custom chip. This is an example of the kind of collaborations we have here. That was developed by Bernhard Boser, who's an analog circuit design legend, and we found that we had this perfect synergy between his group and ours. We have the chip, and that's what drives this stuff. It is a lot of cool stuff. So this is the external circuit. I'll show you the new external circuit, but that's what it was at the time. And here is the moat sutured on. You can't see the sutures because of the resolution of the screen, but it's sutured on to the sciatic nerve of a rat. And we're going to send in, you see the blue TX, we're going to send in ultrasound, and as a function of neural firing, the circuit's going to modulate the piezo, and you'll get some change in reflected signal. I'm going to gloss over the next slide. This is really for those of you that are wondering or work in ultrasound. The message of this whole slide is the amount of ultrasound power we use is ridiculously low. It's so much lower than the FDA limit that there's so much headroom that it's kind of absurd, and we anticipate making use of that headroom as we move forward. But it's really nice because you're not cranking sort of absurd amounts of ultrasound. Now I want to just show you the data. I mean, if you care, the sciatic nerve of a rat is that yellow thing up on the top right, and we did surgery. You see it there. We implanted, close everything up, and then interrogate entirely from the outside. So that's the story. We're going to be listening to all of this from the outside of the rat. And so here's the data. I'll show you 2 slides of data, then future stuff, and we'll wrap up. First off, you can do EMG recording, electromyogram recording, so muscle firing recording, really easily. So what you see in this data, the top left plot is the sort of exact curves of muscle firing signals when taken by wired electrodes. And these wired electrodes are not different from the mode. Actually, they're built into the mode so we can use them as a reference when doing these experiments. So this is the actual gold standard, is the top left. The top right is our reconstructed data from the ultrasound at 10 kilohertz, which is more than fast enough, much faster than you need for EMG. The middle 2 things are the amount of error, and the bottom, if those of you that are physiologists, it's the traditional sigmoidal recruiting curve that you expect to see. As I increase stimulation on the muscle to get it to fire, my recording is showing more and more of these fibers being recruited. This is just sort of a sanity test, like is it doing what we expect it to do? Then we did it on the nerve itself, and again, it's the same stuff. There's the gold standard data, and there you see the reconstructed data, and it's dead on. And it's basically and it's being done at 10 kilohertz, which is wonderful. Okay, so the thing works. I mean, this is kind of the punchline. The thing works. There are limitations to how it worked in this implementation, which I'll tell you a little bit about, and I'll tell you where we're going next. So this is a lot. So let me just walk you through it. The biggest limitation of that study was the noise floor, the effective noise floor. That is to say, what is the smallest signal I can record? And it was on the order of a couple hundred microvolts, which is a lot bigger than you want if you're trying to do single action potential recording in the brain. That was always the big quest. And so while that worked for that application, what we then moved to very quickly is to build a different ASIC that could do less than 10 microvolts recording. That has now returned, and we are in the middle of testing it, and if all goes well, the moat will then be able to record single unit action potentials. At the same time, we're aggressively miniaturizing these moats. Up at the top there, you see a 1 millimeter by 1 millimeter moat. You can see the scale bar there, and then a different version of the moat just below it, which is 3 millimeters, but is built with a different technology. So we're doing a lot of experimentation on what kind of technologies. Some that are not on here include ceramic encapsulation, things that are going to be very relevant for medical devices. And then these pictures on the right are 150 micron test moat being sewn into the nerve, and it disappears into the nerve. At the same time, about a year ago, we began a funded project to build a stimulation version of this. So take the same energy, and instead of backscatter send data on recording, use the energy to stimulate the nerve. That has also returned back. The ASIC design is being led by Ricky Muller, Professor Ricky Muller. And again, that'll be tested, and we anticipate that will have great results using that as a stimulation mode. We have another huge effort on biocompatible materials that have to do with how you coat these things, and we have some really great work that's about to be submitted for publication. And lastly, we have all sorts of miniaturization of that system on the outside. Instead of using the transducer you saw, now the entire thing, this is white little box that fits on the back of the rat. This has been built and tested and works, and then that little head gets placed over wherever the implant is and has the multi-array transducer that can beam steer and account for motion artifact and all sorts of things. So we're pushing hard. The next place we're pushing hard at the very last bullet point there is the central nervous system. I'm not going to talk about that because we're keeping that very close to our chest, but we're pushing very, very hard on using this now in Cortex. Lastly, and this is why I told you at the end I was going to change everything around, we actually think that this has far more applications than anything having to do with neural recording. And the reason is any sensor you want to put on this platform can now be deployed, given, of course, the right constraints and so on, to do something very similar. And so imagine now taking these systems and putting them on kidneys and livers and just sending back oxygen state, temperature. It's sort of like Fitbit for all your internal organs. And we think this is it may be frightening and weird, but this is where it's going. And we think that there's a lot to do here in treating disease. We're taking, it's a huge, serious part of our effort moving forward. I'll give you one example, but more are propping up even as we sort of talk. One example is we have this wonderful project with Mikhail Anwar, which he really approached us and was super excited about, and he's been driving. He's a MD, PhD, Cal, UCSF in oncology radiology, and he said, if we could put these into resected tumor beds and they could keep track of, the first 10,000 cells that come back into a tumor bed, we could have a really big impact on survival rates in certain kind of cancers. And so he's pushing this very aggressively with Christopher Piester, who's another professor here at EECS. There are other examples. Could for example, we were contacted by the head of one of the NIH centers and said, hey, I saw what you guys did. Could you put an oxygen sensor on this and put it into placenta? We could do placental monitoring, which is a really big deal right now, and it's very invasive and very dangerous, but very needed for a lot of things. So we are going to explore this in every direction that we can. We'd love to talk to anybody that has cool ideas or collaborations. And as I said, this is all this IP is being managed, and an entity is sort of being put together to allow people to access this and do all sorts of cool things. With that, I will say thank you. These are all the people that do awesome work and make my life possible. And for amusement value, I'm very proud of this. I have two children, a 10-year-old girl and an 8-year-old boy. That's my daughter at the front, and you can barely tell. Usually when I have more time, I make people hunt for him. But my son is looking off to the left on a rock in the distance. And so I think I have an idea who might be the scientist and who thinks his dad is, I don't know, doing some crazy stuff he doesn't care about at the moment. Anyway, thank you. I can't see, so someone else will have to point because these lights are blinding me.
So as you put more and more motes into people, you're going to hit a bandwidth limit with the amount of information you can just send through ultrasound. How do you plan on dealing with that?
So yeah, that's absolutely true. So ultrasound is limited when compared to EM in terms of bandwidth, right? So if you take a 10 megahertz ultrasound, you can quickly do a calculation on what fraction of that you think you can use for communication. And the answer is that it depends on what your application is. There are so many applications where 10 megahertz bandwidth is more than enough per mote to get data. And so if I have a bunch of them, then it becomes an issue of how your external interrogator deals with all of these 10 megahertz streams, which is a very different problem. But the absolute bandwidth per mote, you're absolutely right. It's going to be limited by, and then there's a trade-off because you can definitely go up higher in ultrasound frequency, right? Medical high-end, super fun medical imaging ultrasound that people have done experimentally goes up into the very high tens of megahertz, right? And so you could imagine doing that, but then your trade-off is penetration depth because it's that many wavelengths, that many more wavelengths that you're doing for a fixed distance. And so there's all these engineering trade-offs, and the answer is the space looks absolutely ripe for all the things I talked about, certainly recording from a handful of channels. I mean, if you think about Recording from neurons, even if you want one channel per neuron and you want to sample at 10 kilohertz into 10 megahertz, that's 1,000. Do some engineering, you know, you're not going to get 1,000x, but let's say you get 500 or 400, that's 400 channels per mode. That's absurd, right? So there's plenty of bandwidth for baseline, the kind of things we talked about. But absolutely, it has less bandwidth than EM, and there will be applications for which maybe you think, I'd rather have a RF hub, right, and all sorts of other things going on because I want to keep the ability to do, you know, 10 gigahertz bandwidth or something. Absolutely. It's just an engineering trade-off, and you pick what space works for you. We're good? Everyone's hungry.